Hello, friend. Tonight we're going somewhere quiet, somewhere ancient, somewhere that's been calling to us since we first learned to look up. Have you ever stood beneath a sky so full of stars that you forgot for a moment where you ended and the universe began? Those pinpoints of light, they're not just decorations scattered across the dark. They're whispers, messages, secrets wrapped in photons that have traveled farther than your mind can comfortably hold. And tonight, we're going to listen to what they're trying to tell us. Because inside every star, there's a story being written in fire and fusion, a story that took billions of years to begin and will take billions more to end, and somehow, against all the silence and distance of space, that story reaches us. It touches our eyes, it warms our skin, it becomes us. What happens inside a star? And why does its light carry the secrets of everything we are? Let's drift into that question together. But before we begin our journey into the heart of Starlight, if you find comfort in these quiet explorations, you might like to stay a while. You can gently tap the like button if this feels like the kind of story you want to hear again. Subscribe if you'd like more nights like this one. And ring the little bell not for noise, but so the next quiet night can find you when you need it most. We're not in a hurry. We never are. Now, let's begin. Imagine this. Every photon of starlight that touches your eye tonight began its journey long before you were born. Some of them started traveling when your great-great-grandparents were children. Others left their stars when the pyramids were still covered in white limestone, gleaming under an Egyptian sun. Light moves fast, the fastest thing in the universe, actually. Scientists measure it at exactly 299,792,458 meters per second. It crosses the distance from Earth to the Moon in just 1.3 seconds. But space is so vast, so impossibly empty, that even light takes years, centuries, millennia to arrive. When you look at Alpha Centauri, the closest star system to our own, you're seeing light that left 4 years ago. When you gaze at Betelgeuse, that red giant flickering in Orion's shoulder, you're seeing light that's been traveling for about 650 years. It left during the Renaissance. Dante had already written his Divine Comedy. The Black Death had already swept through Europe. And here's the thing that scientists discovered slowly, carefully over centuries of watching. That light isn't just light. It's a messenger, a historian, a fingerprint. Every beam carries information about where it came from, what it passed through, what kind of furnace forged it in the first place. Because stars aren't just balls of fire hanging in nothing. That's what people used to think before we knew better. Before we understood that fire needs oxygen and space has none. It's perhaps the most common misconception about stars that they burn like candles or campfires. They don't burn at all, not in the chemical sense. Stars are something stranger, something more elegant. They're forges, engines of creation, alchemical laboratories where the simplest element in the universe, hydrogen, just one proton and one electron, gets squeezed and pressured and heated until it becomes something else, until it becomes light, until it becomes energy, until it becomes eventually us. Think about that for a moment. The calcium in your bones, the iron in your blood, the carbon that forms the backbone of every molecule in your body, none of that existed when the universe began. The Big Bang, about 13.8 billion years ago, gave us mostly hydrogen and helium. That's it. Just the two lightest elements floating in an expanding sea of radiation and time. Everything else, oxygen, nitrogen, sulfur, phosphorus, gold, silver, zinc, all of it was made inside stars, forged in their cores under temperatures reaching 15 million degrees Celsius, and pressures that would vaporize our entire planet in a fraction of a heartbeat. And then those stars died. They exploded or collapsed, or simply exhaled their outer layers into space like a gentle breath. And all those elements, all those building blocks scattered into the cosmic winds. They drifted, they cooled, they clumped together again under gravity's patient pull. And eventually, some of them became a small blue planet orbiting an unremarkable yellow star. And on that planet, after billions of years, those elements arranged themselves into something that could look up at the night sky and wonder where it came from. Carl Sagan used to say, "We are made of star stuff." It's a phrase that's been repeated so often it almost sounds like poetry instead of physics. But it's not metaphor. It's literal truth confirmed by decades of spectroscopic analysis and nuclear physics. The atoms in your left hand probably came from a different star than the atoms in your right. You are a collection of stellar dust held together by forces you can barely perceive, animated by a kind of chemistry so complex it borders on magic. And the light from those distant stars, it's coming home. It's returning to its source just for a moment, just for the brief instant it takes to strike your retina and register in your brain as beautiful or vast or lonely. That's what makes Starlight so haunting, isn't it? It's not just photons bouncing around. It's a reunion, a homecoming written in wavelengths and frequencies. But here's what most people don't realize, that light you see. It didn't just zip straight out of the star's core to your eye. Oh no, the photon that's hitting your eye right now. Let's say it came from our sun, just to keep things close. That photon was born in the sun's core, somewhere between 100,000 and 200,000 years ago. Think about that. The light you're seeing left the center of the sun when woolly mammoths still walked the earth, when Neanderthals were still living in Europe, when our ancestors were just beginning to migrate out of Africa and spread across the world. Why did it take so long? Because the inside of a star is dense, unimaginably dense. The sun's core has a density of about 150 grams per cubic centimeter. That's roughly 150 times denser than water, all crushed into a space where the temperature reaches 15 million degrees Celsius. And every photon that gets created in the fusion's reactions at the core has to fight its way out through layer after layer after layer of atoms. It gets absorbed, re-emitted, absorbed again, scattered, redirected. It ricochets like a pinball in slow motion, taking a random walk that might move it forward a few millimeters, or backward. Scientists call this a drunkard's walk, or a random walk. The photon staggers through the star's interior, bouncing billions upon billions of times, gradually eventually making its way toward the surface. From the core to the surface is about 696,000 kilometers. If that photon could travel in a straight line at the speed of light, it would take just 2.3 seconds. Instead, it takes between 100,000 and 200,000 years. Research published in the Astrophysical Journal suggests the journey depends on the photon's energy and the exact path it takes through the star's radiative and convective zones. But regardless of the specifics, the message is clear. What looks instant to us took epochs to arrive. And then finally, when it reaches the photosphere, the sun's visible surface, it's free. It leaps into space, crosses 150 million kilometers in 8 minutes and 20 seconds, pierces through Earth's atmosphere, and lands on your face during a morning walk. 100,000 years of struggle, then 8 minutes of freedom. Doesn't that make you feel something? Doesn't it change the way you think about sunlight on your skin? That warmth you feel isn't just energy. It's time collapsed into sensation. It's history made tangible. It's a story that started before you, before your species, before almost anything you'd recognize as human. And every star in the sky is telling a similar story. Everyone has its own internal battle, its own journey from core to surface, its own way of converting mass into light. But what is actually happening in there? What's the mechanism? What turns hydrogen into helium and mass into energy and darkness into brilliance? That's the question that haunted scientists for centuries, because for the longest time, we couldn't explain it. We could see the sun. We could measure its light, its heat, its size. We knew it had been shining for a very long time, but we couldn't figure out what kept it burning. In the 1800s, scientists proposed various theories. Maybe the sun was made of coal burning in some kind of chemical reaction. But calculations showed that even if the entire sun were made of coal and somehow had oxygen to burn with, it would only last about 5,000 years. Geologists were already finding rocks much older than that. The great physicist Lord Kelvin in the mid-1800s suggested that maybe the sun was slowly collapsing under its own gravity, and that gravitational contraction was generating heat. The Kelvin-Helmholtz mechanism, as it came to be called, was elegant. It gave you maybe 20 to 30 million years of sunlight, better than coal certainly, but still not enough. Geologists kept finding older rocks. Darwin's theory of evolution required hundreds of millions of years, possibly billions. The numbers didn't add up. Something else was happening, something no one had seen before, something that required a complete reimagining of what matter could do under extreme conditions. The answer came, as many great answers do, from a man who was thinking about something entirely different. Albert Einstein in 1905 published a paper that included one of the most famous equations in history, E sast mc2. Energy equals mass times the speed of light squared. It sounds simple. It looks elegant written on a chalkboard. But the implications were staggering, revolutionary, almost impossible to believe. It meant that mass and energy weren't separate things. They were two forms of the same thing. You could turn a tiny bit of mass into a huge amount of energy, because the speed of light, that c in the equation, is enormous. And when you square it, you get a number so large it almost stops making sense. Let me give you some perspective. 1 kilogram of matter, if you could convert it entirely to energy, would release about 90 petajoules. That's 90 million billion joules of energy. That's roughly equivalent to 21.5 megatons of TNT. That's more than 1,000 Hiroshima bombs. From 1 single kilogram. And stars. Stars are converting millions of tons of mass into energy every single second. Our sun, at this very moment, is turning about 600 million tons of hydrogen into approximately 596 million tons of helium. The difference, about 4 million tons, just vanishes. It becomes light. It becomes heat. It becomes solar wind. It becomes the reason Earth isn't a frozen ball of ice. It becomes the reason you're alive. 4 million tons per second gone into radiation. The sun has been doing this for about 4.6 billion years. And it has enough hydrogen left to keep doing it for another 5 billion years or so, maybe a bit more. When you understand that, really sit with it, you start to realize how impossibly vast these timescales are, how patient the universe is, how slowly and steadily the great engines of creation do their work. There's no rush in a star's core, no urgency, just pressure, heat, and time working together in a dance that's been choreographed by the laws of physics since the beginning. But here's something beautiful. Einstein's equation explained the how of stellar energy, but it took another scientist to explain the what. In the 1920s and 30s, a brilliant British astronomer named Arthur Eddington proposed that stars were powered by nuclear fusion, the process of combining light atomic nuclei into heavier ones. He was right, but he was ridiculed at first. The idea seemed too radical, too impossible. Atoms fusing together, under what conditions? But Eddington persisted. He calculated that the core of the sun must be extraordinarily hot, millions of degrees hot enough to overcome the electromagnetic repulsion between positively charged protons and smash them together. Later, Hans Bethe, a German-American physicist, worked out the exact mechanism in 1939. He described the proton-proton chain reaction that powers stars like our sun. It's a multi-step process where hydrogen nuclei collide, fuse, and eventually build helium-releasing energy at each step. For this work, Bethe won the Nobel Prize in Physics in 1967. And all of that power, all of that transformation was invisible to us until we learned to read the language of light. Because light doesn't just tell us that stars exist, it tells us what they're made of, how hot they are, how old they are, whether they're moving toward us or away from us, whether they're alone or orbited by planets. Every photon is a tiny messenger carrying news from places we'll never touch, times we'll never see, events we can barely imagine. And somehow, impossibly, we learned to decode those messages. In the early 1800s, a German scientist named Joseph von Fraunhofer was studying sunlight through a prism. He noticed something strange, dark lines crossing the rainbow spectrum, hundreds of them, thin, precise, always in the same positions. He didn't know what they were, but he mapped them carefully, cataloging 574 distinct lines. It would take decades before scientists realized what those lines meant. They were the fingerprints of elements. Each chemical element absorbs light at very specific wavelengths. When sunlight passes through the sun's atmosphere, those elements absorb their characteristic wavelengths, leaving dark gaps in the spectrum. By analyzing those gaps, scientists could identify which elements were present in the sun without ever touching it, without ever getting close. It was in essence cosmic detective work, reading messages written in missing colors. And here's something remarkable. In 1868, during a solar eclipse, astronomers noticed a yellow line in the sun's spectrum that didn't match any known element on Earth. They named this mystery element helium, after Helios, the Greek god of the sun. Helium was discovered in the sun before it was discovered on Earth. Think about that. We found an element 150 million kilometers away before we found it in our own atmosphere. It wasn't isolated on Earth until 1895, nearly 3 decades later. That's the power of starlight. It reveals secrets we couldn't find any other way. We learned to split light into its component colors to see the hidden patterns, the missing frequencies, the signatures of elements burning billions of miles away. We learned that stars weren't all the same, that they came in colors, sizes, temperatures, lifetimes. Some are blue and fierce, burning through their fuel in just a few million years. Others are red and cool, smoldering for trillions of years, longer than the current age of the universe. We learned that they were born, lived, and died just like us, only on time scales that make human history look like a single breath. And we learned that we were connected to them. Not metaphorically, not spiritually though, perhaps that too, but physically, chemically, atomically. We learned that we are what happens when starlight remembers itself. So, let me ask you, when was the last time you really looked at the stars? Not just glanced up while walking to your car, but actually stopped and stared. Let your eyes adjust to the darkness. Let the silence settle around you. If you haven't done it in a while, maybe tonight would be a good night. Pick a star, any star. Let your eyes rest on it for a moment. And know that the light entering your eye left that star years ago, maybe centuries ago, maybe even millennia ago. If you're looking at something truly distant, it crossed an ocean of space so vast that even our fastest spacecraft would take thousands of years to make the journey. But light made it. And now it's here completing the final step of a voyage that began in nuclear fire. And in a very real way, that star is touching you. Its light is interacting with the atoms in your retina atoms that were made in another star long ago in another corner of the galaxy. It's a reunion of sorts, a quiet hello between relatives who have never met, separated by unimaginable distances, but connected nonetheless by the simple fact of existing. That's the secret hidden in starlight. That's the story it's been trying to tell us all along. We are not separate from the stars. We are not strangers in the cosmos. We are the universe looking at itself through eyes made of its own dust, illuminated by its own light. And if that doesn't make you feel a little less alone in the dark, then perhaps nothing will. But we've only touched the surface of this story. We know that stars create light, that light carries secrets, that those secrets connect us to something vast and ancient. But where do stars come from in the first place? What makes them ignite? What turns a cloud of cold, dark gas, floating silent in the void, into a blazing furnace that will shine for billions of years? That's where we're drifting now. Into the nurseries, into the places where gravity and time conspire to birth new suns from nothing but dust and darkness, and the patient pull of forces we're only beginning to understand. In the beginning, there was darkness, not the comfortable darkness of a bedroom at night, or the soft darkness behind closed eyelids. This was the darkness of emptiness, of cold, of silence so complete it felt like the absence of possibility itself. And yet, somehow from that darkness, stars were born. How does nothing become something? How does cold become fire? How does silence become light? That's the question we're drifting into now. Picture space between the stars, not the space near Earth where satellites orbit and astronauts float, but deep space, the space between star systems, between galaxies even. It's not empty. That's the first thing astronomers realized when they started looking carefully. What appears to be void is actually filled with something. Thin, yes, incredibly thin, but present nonetheless. Scientists call these regions molecular clouds, or nebulae. They're made mostly of hydrogen gas, about 70% by mass, with some helium mixed in, maybe 28%, and tiny traces of heavier elements. Carbon, oxygen, nitrogen dust grains made of silicates and frozen water. The density is almost incomprehensibly low. In the densest parts of these clouds, you might find 10,000 to 100,000 molecules per cubic centimeter. That sounds like a lot, until you realize that the air you're breathing right now contains about 25 quintillion molecules per cubic centimeter. These clouds are, by terrestrial standards, better vacuums than anything we can create in a laboratory. And yet, they're the nurseries of stars, the birthplaces of suns. How? The answer, as with so many things in the universe, comes down to gravity. Gravity is patient. It's weak compared to the other forces of nature: electromagnetic force, strong nuclear force, weak nuclear force. But it has one crucial advantage: it never stops pulling. It never cancels out. It just accumulates slowly, quietly, over time. In a molecular cloud, every atom pulls on every other atom. Most of the time, this pulling doesn't do much. The cloud is in equilibrium. The outward pressure from the gas's thermal motion balances the inward pull of gravity. Everything stays spread out, diffuse, stable. But sometimes, something tips the balance. Maybe a nearby star explodes in a supernova, sending a shock wave through the region. Maybe two clouds collide as they orbit the galaxy. Maybe the cloud just grows massive enough, slowly accumulating more gas until gravity finally wins. Whatever the trigger, a region of the cloud starts to collapse. At first, it's subtle, a slight increase in density, a gentle gathering, but gravity is a runaway process. As matter clumps together, the gravitational pull gets stronger. Stronger pull means faster collapse. Faster collapse means even more clumping. The cloud fragment begins to fall in on itself. And as it falls, something remarkable happens. It heats up. This might seem counterintuitive. How does collapse create heat? Isn't space cold? It is. But when you compress a gas, you do work on it. You force its atoms closer together. They move faster. Temperature, after all, is just a measure of how fast atoms are moving. Compress them, and they speed up. Speed them up, and they get hotter. This is called gravitational heating, and it's the same principle that makes a bicycle pump warm when you compress air into a tire. As the cloud collapses, the center gets denser and hotter. We call this early stage a protostar. It's not a star, yet fusion hasn't started, but it's on its way. The protostar is hidden buried deep inside a cocoon of gas and dust. From the outside, you couldn't see it glowing, not with visible light. But if you looked with infrared cameras, the kind that detect heat, you'd see it shining. A warm spot in the cold, a promise of fire to come. One of the most famous examples of a stellar nursery is the Orion Nebula, located about 1 to 350 light-years from Earth in the constellation Orion. It's visible to the naked eye as the middle star in Orion's sword, but through a telescope, it reveals itself as a vast glowing cloud of gas and dust stretching about 24 light-years across. The Hubble Space Telescope has taken stunning images of the Orion Nebula, showing hundreds of protostars in various stages of formation. Some are just beginning to collapse. Others are already surrounded by disks of material that will eventually form planets. It's a cosmic maternity ward delivering new suns into the universe. But not all protostars make it to full starhood. Some never gather enough mass. They remain brown dwarfs, objects too small to ignite fusion, too big to be called planets. They glow faintly from the heat of their formation, then slowly cool over billions of years, fading into darkness. To become a true star, a protostar needs to reach a critical mass at least about 0.08 solar masses, or roughly 80 times the mass of Jupiter. Below that threshold, the core never gets hot enough or dense enough for fusion to begin. But if the protostar does gather enough mass, if it keeps pulling in gas from the surrounding cloud, then something extraordinary happens. The core temperature climbs 1,000 Kelvin, 10,000 Kelvin, 100,000 Kelvin. The pressure builds. Atoms are stripped of their electrons, creating a plasma, a sea of positively charged nuclei and free-floating electrons. And still, the collapse continues. Still, gravity pulls inward, until finally, the core reaches about 10 million Kelvin. At that temperature, hydrogen nuclei protons are moving so fast that when they collide, they can overcome their electromagnetic repulsion. Remember, protons are positively charged and like charges repel. Under normal conditions, they'd bounce off each other. But at 10 million Kelvin, they're moving at about 500 kilometers per second. Fast enough to get close enough for the strong nuclear force to take over. And when that happens, they fuse. Two protons combine to form deuterium-heavy hydrogen, releasing a positron and a neutrino in the process. The deuterium fuses with another proton to form helium-3. Two helium-3 nuclei collide to form helium-4, spitting out two protons in the process. Net result: 4 hydrogen nuclei become 1 helium nucleus plus energy. A lot of energy. This is the moment a star is born, the moment fusion ignites, the moment gravity's long patient work finally pays off. The protostar becomes a star. The process from initial collapse to fusion ignition takes time. For a star like our Sun, it's about 50 million years. For more massive stars, it's faster, maybe 100,000 years. For smaller stars, it's slower, hundreds of millions of years. But however long it takes, the result is the same. A new light appears in the universe. A new furnace begins its work of turning hydrogen into helium mass, into energy darkness, into brilliance. And here's something most people don't realize. Once fusion starts, it stops the collapse. The energy released by fusion creates an outward pressure radiation and pressure that pushes back against gravity's inward pull. The star reaches a balance, a stable equilibrium, where the force pulling in equals the force pushing out. Astronomers call this hydrostatic equilibrium, and it's the defining characteristic of a main sequence star. For as long as there's hydrogen in the core to fuse, the star stays balanced, stable, shining steadily. Our Sun has been in this balanced state for 4.6 billion years. It will remain there for another 5 billion years or so. Think about that stability, that patience. The universe creates these engines and lets them run unchanged for timescales that dwarf all of human history. The sun was shining before the earth formed. It was shining when the first life emerged in ancient oceans. It was shining when dinosaurs walked the land, when ice ages came and went, when our ancestors first looked up and wondered what those lights in the sky might be. And it will keep shining long after we're gone, assuming we don't figure out how to survive as a species. Long after our cities have crumbled to dust. Long after the continents have drifted into unrecognizable configurations. The sun doesn't care about us. It's not aware of us. It's just doing what physics requires, converting mass to energy slowly and steadily for eons. There's something both humbling and comforting about that isn't there. But here's a question. If stars form from collapsing gas clouds, why aren't they all the same size? Good question. The answer is that the initial conditions matter. How much mass was in the cloud fragment that collapsed? How fast was it rotating? Was it disturbed by nearby stars or supernova shock waves? All these factors influence the final mass of the star. The smallest stars that can sustain fusion are red dwarfs, weighing in at about 0.08 solar masses. They're cool, dim, and incredibly long-lived. A red dwarf might burn for 10 trillion years, 1,000 times longer than the current age of the universe. None of the red dwarfs that formed in the early universe have died yet. They're all still shining slowly, patiently, waiting for their time to come. At the other extreme, you have massive stars, 50, 100, even 200 times the mass of the sun. These are the blue supergiants, the hypergiants, the luminous beasts that burn through their fuel in just a few million years. They live fast and die young, exploding as supernovae and leaving behind neutron stars or black holes. Why the difference in lifespan? It comes down to how much fuel you have and how fast you're burning it. Massive stars have more hydrogen. Yes, but they also burn it much, much faster. The fusion rate in a star's core increases dramatically with mass. A star 10 times the sun's mass might be 10,000 times more luminous. It's not burning 10 times as much fuel, it's burning 10,000 times as much. So, it runs out sooner, much sooner. It's like the difference between a candle and a bonfire. The bonfire is brighter, warmer, more impressive, but it consumes its wood much faster than the candle consumes its wax. Red dwarfs are candles. Blue supergiants are bonfires. Both are stars. Both are fusing hydrogen into helium. But their timescales, their fates, their impacts on the galaxy, all completely different. Now, here's something that confused astronomers for a long time. If stars form from collapsing gas clouds, why don't they collapse all the way down into black holes immediately? What stops the collapse once it starts? For a long time, this was a mystery. Scientists knew that protostars heated up as they collapsed. They could measure the infrared glow, but they couldn't quite explain why the collapse didn't just keep going faster and faster until everything crunched down into a singularity. The answer, it turns out, is angular momentum. Almost everything in space is rotating at least a little bit. The gas cloud is rotating as it orbits the galaxy. When it starts to collapse, that rotation speeds up, just like a figure skater spinning faster when they pull their arms in. As the rotation speeds up, centrifugal force starts to matter. It creates an outward push that resists the inward pull of gravity, but only in the plane perpendicular to the rotation axis. The result? The collapsing cloud flattens into a disk. Matter can still fall inward along the rotation axis, the poles, but in the equatorial plane, it piles up, forming a rotating disk around the protostar. This is called an accretion disk. And here's where it gets interesting, that disk is the birthplace of planets. The same process that forms a star also forms a planetary system. The leftover gas and dust in the disk gradually clumps together under gravity, forming larger and larger bodies. Dust grains stick together into pebbles. Pebbles collide to form rocks. Rocks accumulate into planetesimals. Planetesimals grow into planets. Our solar system formed this way. So did every other planetary system we've discovered. In 1995, astronomers Michael Mayor and Didier Queloz discovered the first exoplanet orbiting a sun-like star, 51 Pegasi b. It was a Jupiter-sized planet orbiting incredibly close to its star, completing one orbit in just 4.2 days. This discovery revolutionized astronomy. It proved that our solar system wasn't unique. It showed that planet formation was common, perhaps even inevitable. Since then, we've discovered over 5,000 exoplanets, with thousands more candidates waiting to be confirmed. Almost every star we look at closely seems to have planets, which means almost every star formed from a collapsing cloud with a rotating disk. Almost every star went through this same process: gravitational collapse, heating, disk, formation, fusion, ignition, planetary system formation. It's a pattern repeated billions upon billions of times throughout the universe. But Let's return to the moment of ignition, that first fusion reaction, that first release of energy. What does it look like? From the outside, not much changes at first. The protostar is still buried in its cocoon of gas and dust, but deep in the core, photons are being created. High-energy gamma rays born from the fusion of hydrogen into helium. Those photons start their long, slow journey outward. They bounce and scatter, absorbed and re-emitted, gradually working their way toward the surface over hundreds of thousands of years. And as they travel, they push. Radiation pressure builds up. It starts to clear out the surrounding gas and dust, like a wind blowing away fog. Eventually, the protostar becomes visible. Its light escapes the cocoon, and for the first time, it can be seen a new star shining in the darkness. Astronomers have watched this happen. With infrared telescopes, they can see protostars buried in dust. Then years or decades later, the dust clears and a visible star appears. It's like watching a butterfly emerge from a cocoon, except the butterfly weighs 1,000,000 trillion kilograms and will shine for billions of years. There's something deeply moving about witnessing a birth, even if it's the birth of something so alien, so vast, so far beyond human scale. Because in that moment, you're seeing the universe creating itself. You're watching matter organizing into structure chaos, giving way to order, potential becoming actual, and you realize this is how everything began. This is how our sun formed. This is how the elements in your body were forged. This is the process that made life possible. Without stellar birth, there would be no planets, no chemistry, no evolution, no consciousness, no one to look up at the sky and wonder. Stellar birth is in a very real sense the beginning of everything that matters. So, the next time you see a nebula in a photograph, the Eagle Nebula, the Carina Nebula, the Orion Nebula, remember, you're not just looking at a pretty cloud of gas. You're looking at a nursery, a factory, a place where gravity and time are conspiring to create new suns, new worlds, new possibilities. You're looking at the universe in the act of creation. And somewhere in those clouds, hidden from view, a new star is igniting for the first time. Its core is reaching 10 million Kelvin. Hydrogen is beginning to fuse. Photons are beginning their long journey outward. In a few 100,000 years, that star will emerge. It will shine. It will warm any planets that form around it. And maybe billions of years from now, something on one of those planets will look up at its sky and wonder, how did we get here? And the answer always will lead back to this moment, to dust and darkness, to gravity and patience, to the slow, steady collapse that turns nothing into everything. But we've only seen the birth. We've only watched the ignition. We haven't yet looked inside. We haven't yet understood the machinery, the specific step-by-step process that turns hydrogen into helium mass, into energy potential, into light. That's where we're going next, into the heart of the furnace itself, into the dance of atoms that powers everything. Deep in the core of a star, something impossible is happening. Particles that should repel each other are colliding, merging, becoming something new. And in that transformation, they're releasing more energy than anything else in the universe. This is fusion, the dance that powers the stars, the alchemy that turns the simplest element into something heavier and mass into pure light. But how does it actually work? What's really happening down there in the darkness, where no telescope can see, where temperatures rage at 15 million degrees? Let's descend into that furnace together. Imagine you're holding two magnets North Pole to North Pole. You can feel them pushing against each other, resisting. The closer you try to bring them together, the harder they push back. Now, imagine those magnets are 1 billion times stronger, and imagine you need to force them so close together that they actually touch, actually merge into one. That's essentially what fusion requires. Protons, the nuclei of hydrogen atoms, are positively charged. And positive charges repel each other through electromagnetic force. It's one of the fundamental rules of physics. Like charges push apart. To make two protons fuse, you have to overcome that repulsion. You have to force them close enough that another force, the strong nuclear force, can take over. The strong force is, as its name suggests, very strong, but it only operates at extremely short ranges, about 10 or 15 meters. That's a femtometer, a millionth of a billionth of a meter. Get two protons within that distance, and the strong force binds them together. But getting them that close, that requires extraordinary conditions. Specifically, it requires the core of a star at 15 million Kelvin. The temperature in our sun's core protons are moving at about 500 kilometers per second. That's fast enough that when they collide, there's a small chance they can get close enough for the strong force to grab hold. But here's the thing, even at those speeds, even at those temperatures, fusion is rare. Most collisions don't result in fusion. Most of the time, the protons just bounce off each other. The electromagnetic repulsion wins. For fusion to occur, the protons need to quantum tunnel through the electromagnetic barrier. Let me explain what that means. In classical physics, the physics of everyday objects, the physics Newton described, if you don't have enough energy to climb over a hill, you can't get to the other side. You're stuck. But in quantum mechanics, the physics of tiny particles, there's a strange loophole. Even if you don't have enough energy to climb the hill, there's a small probability you can appear on the other side anyway. It's called quantum tunneling, and it's one of the weirdest, most counterintuitive predictions of quantum theory. And it's absolutely essential for stars to work. If protons had to actually overcome the electromagnetic repulsion through sheer kinetic energy alone, they'd need to be moving much, much faster. The core would need to be billions of degrees hotter. But thanks to quantum tunneling, fusion can happen at only 15 million degrees. The protons get close, not quite close enough, but close enough that there's a tiny probability they can tunnel through the barrier and fuse. That probability is incredibly small. For any given proton in the sun's core, it takes an average of about 10 billion years before it successfully fuses with another proton. 10 billion years. And yet, because there are so many protons in the sun's core, about 10 or 56 of them, billions upon billions of fusions are happening every second. It's a game of astronomical numbers. Tiny probability multiplied by vast quantity equals steady power output. The sun converts about 600 million tons of hydrogen into helium every second, remember. That's the result of countless individual fusion reactions, each one rare, each one unlikely, but collectively inevitable. Now, let's talk about the actual mechanism, the step-by-step process by which hydrogen becomes helium. For stars like our sun, the primary process is called the proton-proton chain reaction. It was worked out in detail by Hans Bethe in 1939, and it earned him the Nobel Prize in Physics in 1967. Here's how it works. Step 1. Two protons collide and fuse. One of them converts into a neutron through a process called beta plus decay, emitting a positron and a neutrino. The result is deuterium-heavy hydrogen, a nucleus with one proton and one neutron. This is the slowest step, the bottleneck. This is the step that takes on average 10 billion years per proton. Once you have deuterium, the rest happens relatively quickly. Step 2. The deuterium nucleus collides with another proton and fuses, forming helium-3, a nucleus with two protons and one neutron. A gamma-ray photon is released. This step takes only about 6 seconds on average. 6 seconds compared to 10 billion years. The contrast is staggering. Step 3. Two helium-3 nuclei collide and fuse, forming helium-4, the common stable form of helium with two protons and two neutrons. Two protons are ejected in this reaction, and they're free to participate in future reactions. Net result, 4 hydrogen nuclei go in. 1 helium-4 nucleus comes out. Plus energy. How much energy? Each complete proton-proton chain releases about 26.7 million electron volts of energy. That might not sound like much. An electron volt is a tiny unit. But remember, this is happening billions upon billions of times per second. The total energy output of the sun is about 3.8 x 10 × 26 watts. That's 380 septillion watts every second. For context, all of human civilization currently uses about 18 terawatts of power. That's 18 trillion watts. The sun produces about 20 billion times more energy than all of humanity uses every second. And it's been doing this steadily for 4.6 billion years. It's hard to wrap your mind around numbers like that, hard to feel the scale. But maybe this helps. The energy that hits Earth from the sun in 1 hour is more than all of humanity uses in an entire year. We're bathed in abundance. We're living in the overflow of a fusion reactor that never sleeps, never slows, never stops. Now, here's something interesting. The proton-proton chain is the main fusion pathway for stars like the sun. But for more massive stars more than about 1.3 times the sun's mass, there's a different pathway that dominates. It's called the CNO cycle. CNO stands for carbon, nitrogen, oxygen. Wait, you might be thinking, I thought we were fusing hydrogen into helium. What does carbon have to do with it? Good question. In the CNO cycle, carbon acts as a catalyst. It's not consumed in the reaction, it's recycled. But its presence speeds up the fusion process dramatically. Here's how it works. A carbon-12 nucleus captures a proton, becoming nitrogen-13. The nitrogen-13 decays into carbon-13. The carbon-13 captures another proton, becoming nitrogen-14. The nitrogen-14 captures a third proton, becoming oxygen-15. The oxygen-15 decays into nitrogen-15. And finally, the nitrogen-15 captures a fourth proton, splits into carbon-12 and helium-4. The carbon-12 is back where it started. The net result is the same as the proton-proton chain. 4 hydrogens become 1 helium plus energy. But the CNO cycle is much faster at high temperatures. Above about 17 million Kelvin, it dominates over the proton-proton chain. This means massive stars, which have hotter cores, generate their energy primarily through CNO fusion. The existence of the CNO cycle was proposed by Hans Bethe and Carl Friedrich von Weizsäcker independently in 1938 and 1939. It was a remarkable insight. The idea that elements like carbon could act as catalysts for stellar fusion, that the universe's chemistry could influence its nuclear physics. Now, let's talk about what happens to the energy once it's created. When fusion occurs, it releases energy in several forms. There are gamma-ray photons, high-energy light. There are neutrinos, ghostly particles that barely interact with anything. And there's kinetic energy. The helium nucleus and any other particles released are moving fast, carrying energy in their motion. The neutrinos escape immediately. They barely notice the star is there. They pass through the entire mass of the sun, 333,000 Earth masses of dense plasma, as if it were empty space. 8 minutes later, they're streaming past Earth. Most of them pass right through Earth too, and out the other side, never interacting with a single atom. Right now, as you're listening to this, billions of neutrinos from the sun are passing through your body every second. You don't feel them. They don't do anything. They're just passing through. Scientists have built massive detectors deep underground to catch a handful of these neutrinos. The detectors use thousands of tons of water or other materials, waiting patiently for the incredibly rare moment when a neutrino actually interacts with an atom. And when they do detect neutrinos from the sun, it confirms our theories about fusion. The neutrinos carry direct information from the core, from the fusion reactions happening right now. Unlike photons, which take hundreds of thousands of years to reach the surface, neutrinos arrive in 8 minutes. They're messengers from the heart of the star. But most of the energy doesn't escape as neutrinos. Most of it comes out as photons and kinetic energy, and that energy stays trapped in the star, bouncing around, heating the plasma, creating pressure. That pressure is crucial. It's the pressure that holds the star up against gravity's crushing pull. Remember, gravity is always trying to make the star collapse. The only thing stopping it is the outward pressure from the hot plasma, which is ultimately powered by fusion in the core. As long as fusion continues, the star stays balanced, stable, shining. This balance is called hydrostatic equilibrium, and it's the reason stars last so long. Once a star reaches the main sequence, once fusion ignites and the star settles into stability, it can shine for billions of years without significant change. Our sun is about halfway through its main sequence lifetime. It's been stable for 4.6 billion years. It will remain stable for another 5 billion or so. Think about what that means. Think about the steadiness, the reliability, the patience. Every day for 4.6 billion years, the sun has converted hydrogen to helium. Every day it's released the same amount of energy, give or take small fluctuations. Every day it's balanced gravity and pressure darkness and light collapse and expansion. It's not conscious. It doesn't choose to do this. It's just following the laws of physics, the equations that govern matter and energy. And yet there's something almost miraculous about it. About the fact that such stability is possible, that the universe contains these engines that can run for billions of years without breaking down. Now let's address a common misconception. People sometimes confuse fusion with fission. They're both nuclear processes, both involve atomic nuclei, both release energy. But they're fundamentally different. Fission is the splitting of heavy nuclei into lighter ones. It's what happens in nuclear power plants and atomic bombs. You take a large nucleus like uranium-235, hit it with a neutron, and it splits into smaller pieces, releasing energy and more neutrons in the process. Fusion is the opposite. It's the combining of light nuclei into heavier ones, hydrogen into helium, and eventually in the later stages of a star's life, helium into carbon into oxygen, and so on, up the periodic table. Both processes release energy, but for different reasons. Fission releases energy because large nuclei are less stable than medium-sized ones. When you split uranium into smaller pieces, you end up with nuclei that are more tightly bound, more stable. The difference in binding energy is released. Fusion releases energy because small nuclei are less stable than medium-sized ones. When you combine hydrogen into helium, you get a nucleus that's more tightly bound. Again, the difference is released as energy. There's a sweet spot in the middle of the periodic table, around iron 56, where nuclei are most stable. Fusing elements lighter than iron releases energy. Splitting elements heavier than iron releases energy. But fusing elements heavier than iron, that costs energy. It doesn't happen naturally in stars during their normal lifetimes. Which raises an interesting question. If stars can't fuse elements heavier than iron through normal fusion, where did all the heavy elements in the universe come from? Where did the gold and jewelry come from? The uranium in nuclear reactors, the lead in old paint. The answer is supernovae and neutron star collisions. Violent events that create conditions so extreme, so energetic, that even energy-costing reactions can occur. But we're getting ahead of ourselves. That's a story for later. For now, we're still in the core, still watching the dance of fusion, still marveling at the elegant balance that keeps a star shining. Let me give you one more piece of perspective. Humans have been trying to recreate fusion on Earth for over 70 years. We want to build fusion reactors that can generate clean, abundant energy without the radioactive waste of fission reactors. And it's hard, incredibly hard. The problem is containment. To get fusion to occur, you need to heat hydrogen to tens of millions of degrees. At those temperatures, no solid material can contain it. Everything would instantly vaporize. So, scientists use magnetic fields to contain the plasma, keeping it suspended in space, never touching the walls of the reactor. Facilities like ITER in France and NIF in California are pushing the boundaries of what's possible. In December 2022, the National Ignition Facility achieved a major milestone. They got more energy out of a fusion reaction than they put in to trigger it. It was the first time in history that human-made fusion achieved net energy gain. It's a huge step forward, but we're still far from practical fusion power. The reaction lasted only a fraction of a second. The energy gain, while significant, was still small, and the amount of energy needed to power the lasers that triggered the reaction was much larger than the energy released by the fusion itself. Stars make it look easy. They do it effortlessly, continuously for billions of years. But that's because stars have something we don't: gravity. Gravity provides the confinement. Gravity creates the pressure. Gravity does all the hard work of holding everything together and keeping the core hot and dense. We have to use magnetic fields and lasers and superconducting magnets and cryogenic cooling and all sorts of complex engineering to try to recreate even a tiny fraction of what happens naturally in a star's core. It's humbling, really. The universe has been running fusion reactors for over 13 billion years. We've been trying for less than a century, and we're still figuring out the basics. But we're learning. Slowly, patiently, we're learning. And maybe someday we'll have fusion power plants. Clean energy from the same process that powers the stars. Energy so abundant that scarcity becomes a memory. It's a beautiful thought, isn't it? That we might one day hold a piece of the sun's power in our hands here on Earth, contained and controlled and used to build a better world. But even if we succeed, even if we master fusion, we'll only be copying what the universe has been doing all along. The stars got there first. The stars showed us it was possible. And every photon of sunlight, every moment of warmth on your skin is a reminder of that ongoing fusion, that dance of atoms in the dark, that transformation of hydrogen into helium, mass into energy, potential into light. It's happening right now, this very second. 4 million tons of matter becoming pure energy in the sun's core. And 8 minutes from now, a tiny fraction of that energy will arrive here. It will warm the oceans, feed the plants, power the weather, make life possible. All because protons learn to dance close enough to touch. All because quantum mechanics allows the impossible to happen just rarely enough to last billions of years. All because the universe found a way to turn darkness into light. Now that we understand the engine, the mechanism that generates the energy we need to understand the structure, because fusion only happens in the core, but the energy has to travel outward somehow. It has to cross hundreds of thousands of kilometers of dense plasma to reach the surface. And that journey is a story all its own. One of pressure and radiation of zones and layers of a structure so precisely organized, it almost seems designed. A star is not uniform. If you could slice through one, cut it open like an apple, you wouldn't find the same material all the way through. You'd find layers, zones, regions with different temperatures, different densities, different ways of moving energy outward. It's organized, structured, almost architectural in its precision. And each layer has its own story, its own physics, its own relationship with light and time. Let's peel back those layers one by one and see what secrets they hold. Imagine you're a photon born in the core of the sun from a fusion reaction. You emerge as a gamma ray, the highest energy form of light, traveling at 300,000 kilometers per second, ready to escape into space. How long do you think it would take to reach the surface? The sun's radius is about 696,000 kilometers. If you could travel in a straight line, you'd reach the surface in about 2.3 seconds. Simple math, right? Except you can't travel in a straight line, not through the interior of a star, because every few millimeters you're going to hit something, an electron, an ion, another particle, and when you do, you'll be absorbed then re-emitted in a random direction. Maybe forward, maybe backward, maybe sideways. Completely random. This is the photon's journey through the radiative zone, and it's one of the most remarkable processes in stellar physics. Let's start at the beginning. At the core. The core is where fusion happens. It's roughly the innermost 25% of the sun's radius, about 175,000 kilometers across. The temperature there is approximately 15 million Kelvin. The density is about 150 grams per cubic centimeter, roughly 150 times denser than water. Under those conditions, matter exists as plasma. Electrons have been stripped from their atoms by the intense heat. What remains is a sea of positively charged nuclei and free-floating electrons, all moving at tremendous speeds. And in that sea, fusion is occurring. Hydrogen is becoming helium. Energy is being released. But that energy needs to get out. It needs to travel from the core to the surface, where it can finally escape as sunlight. The question is, how immediately surrounding the core is the radiative zone? It extends from about 25% of the sun's radius out to about 70%, roughly from 175,000 kilometers to 490,000 kilometers from the center. In this zone, energy moves primarily by radiation. Photons are created, absorbed, re-emitted, absorbed again over and over in an endless cycle. The plasma in the radiative zone is still incredibly dense enough that photons can't travel far before they interact with something. On average, a photon in the sun's radiative zone travels only about 1 centimeter before being absorbed. 1 centimeter. Then it's absorbed by an electron or an ion, which heats up slightly. A tiny fraction of a second later, that particle emits a new photon. But the new photon is traveling in a random direction, and it's usually slightly lower in energy, shifted toward longer wavelengths. So the gamma ray from the core gradually transforms as it travels. Gamma ray becomes X-ray. X-ray becomes ultraviolet. Ultraviolet becomes visible light. Visible light becomes infrared. By the time the energy reaches the surface, it's been degraded from high-energy gamma rays into mostly visible and infrared light, the kind of light our eyes can see, the kind of light that warms our skin. This process, this random walk, takes time, a lot of time. Scientists estimate that for a photon to make its way from the sun's core to the edge of the radiative zone takes somewhere between 50,000 and 200,000 years. Some estimates go as high as 1,000,000 years. The exact number depends on the path the photon takes, the number of absorptions and emissions, the density profile of the star. But regardless of the details, the message is clear. Light moves slowly through the radiative zone. Not because it's traveling slowly, it's always moving at light speed between interactions, but because the path is so convoluted, so twisted, so full of detours and backtracking. It's like trying to walk in a straight line through a dense forest while blindfolded, taking a step, bumping into a tree, turning randomly, taking another step. You might end up going backward as often as forward. Mathematically, scientists describe this as a random walk or diffusion process. The distance you travel scales with the square root of the number of steps, not linearly with the number of steps. So even though each individual step is tiny 1 centimeter, and even though you're taking steps at the speed of light, the net progress outward is incredibly slow. This is why the sunlight hitting your face right now is ancient. The energy in those photons was created deep in the sun's core, tens of thousands of years ago, maybe hundreds of thousands of years ago, when humans were still learning to make fire, when mammoths still roamed, when the last ice age was beginning or ending. That energy has been trapped inside the sun all this time, slowly working its way outward, bouncing and scattering, gradually making progress toward freedom. And now, finally, it's here. It's warming you. It's lighting your world. After a journey that spanned epochs, doesn't that change how you think about a sunny day? But the radiative zone isn't the whole story, because eventually, as you move outward, conditions change. At about 70% of the sun's radius, about 490,000 kilometers from the center, something shifts. The temperature has dropped to about 2 million Kelvin. The density has decreased. And suddenly radiation is no longer the most efficient way to transport energy. Convection takes over. Welcome to the convective zone. In the convective zone, energy moves not through individual photons bouncing around, but through bulk motion of the plasma itself. Hot plasma rises, cool plasma sinks. It's like boiling water. or the way air moves in Earth's atmosphere, creating winds and weather patterns. Here's why this transition happens. In the deeper layers of the sun, the plasma is so hot and dense that it's almost completely ionized. Electrons are stripped from atoms, and ionized plasma is relatively transparent to radiation. Photons can move through it slowly, yes, but they can move. But as you move outward and the temperature drops, electrons start recombining with nuclei. Partially ionized atoms form. And these partially ionized atoms, especially heavy elements like iron, are very good at absorbing photons. The plasma becomes more opaque. Photons can't travel as freely. The radiative transport becomes inefficient. When that happens, nature finds another way. Convection. Hot plasma at the bottom of the convective zone absorbs energy. It heats up, becomes less dense, and rises. As it rises, it carries its energy upward. When it reaches cooler regions near the surface, it releases that energy, cools down, becomes denser, and sinks back down. The cycle repeats over and over, creating convection cells, circulating loops of plasma that carry energy from the base of the convective zone to the surface. This process is much faster than radiative diffusion. A blob of plasma can make the journey from the base of the convective zone to the surface in about a week or two. Compare that to the hundreds of thousands of years it took to cross the radiative zone, and you can see why convection is so efficient. The convective zone extends from about 70% of the sun's radius all the way to the surface, from about 490,000 kilometers to 696,000 kilometers. And you can actually see convection happening if you look at the sun through a telescope with proper solar filters. Never look directly at the sun without protection. It will damage your eyes permanently. But with the right equipment, you can see the sun's surface, the photosphere, covered in a pattern that looks like granules or cells. These granules are the tops of convection cells. Each one is about 1,000 kilometers across. Hot plasma rises in the center of each granule, spreads outward, cools, and sinks along the edges. The entire surface of the sun is constantly churning with this motion. It's not still, it's not calm, it's boiling. And this convection has consequences beyond just transporting energy. It also generates the sun's magnetic field. Inside the convective zone, the moving plasma, which is electrically charged, creates electric currents. And electric currents generate magnetic fields. The complex, turbulent motion of convection twists and tangles these magnetic fields, amplifying them, creating loops and knots that eventually break through the surface. When they do, they create sunspots, solar flares, coronal mass ejections, all the dynamic, violent phenomena we associate with solar activity. So, the sun's weather, in a sense, is driven by convection, by the boiling motion of plasma in the outer layers. Now, let's talk about the surface itself, the photosphere. The word photosphere comes from Greek photo, meaning light, sphere, meaning ball. It's the sphere of light, the layer where photons finally escape. The photosphere is only about 500 kilometers thick, paper thin, compared to the sun's total radius. It's the layer we see when we look at the sun. It's where the plasma becomes transparent enough that photons can finally travel freely into space. The temperature at the photosphere is about 500 Kelvin. That's much cooler than the interior, of course, but still hot enough to vaporize any known material. It's hot enough to emit light in the visible spectrum, the characteristic yellow-white color of sunlight. And once photons leave the photosphere, they're free. They travel through space at light speed, crossing the 150 million kilometers to Earth in just 8 minutes and 20 seconds. After hundreds of thousands of years trapped inside the sun, the final leg of the journey takes 8 minutes. Freedom, when it comes quickly. But the photosphere isn't quite the edge of the sun. There are more layers beyond it, layers that are harder to see because they're much thinner and fainter. Just above the photosphere is the chromosphere, a layer about 2,000 kilometers thick. The name comes from chromo, meaning color, because during a solar eclipse, when the bright photosphere is blocked by the moon, The chromosphere appears as a thin reddish ring around the sun. That red color comes from hydrogen emission, specifically hydrogen alpha light at a wavelength of 656 nanometers. The chromosphere is hotter than the photosphere, reaching temperatures of about 20,000 Kelvin. This might seem strange. Why would temperature increase as you move away from the heat source? The answer is still debated, but most scientists believe it has to do with magnetic energy and acoustic waves. Energy from the convective zone below creates waves and magnetic disturbances that propagate upward, depositing their energy in the chromosphere and heating it. And beyond the chromosphere lies the corona, the sun's outer atmosphere. The corona is where things get really strange. It extends millions of kilometers into space, gradually fading into the solar wind. And its temperature, about 1 to 3 million Kelvin. Yes, you read that right. The corona is hotter than the photosphere, much hotter. This is called the coronal heating problem, and it's one of the unsolved mysteries of solar physics. How does the corona so far from the fusion core maintain temperatures higher than layers much closer to the heat source? The leading theory involves magnetic fields again. The sun's magnetic field lines thread through the corona, and they're in constant motion, tangling and reconnecting. When magnetic field lines reconnect, they release enormous amounts of energy in the form of heat and accelerated particles. This process, called magnetic reconnection, is also responsible for solar flares, some of the most powerful explosions in the solar system. A single large solar flare can release as much energy as 1 billion atomic bombs in a matter of minutes. And all of this, the photosphere, chromosphere, corona, magnetic activity, solar wind, all of it is powered ultimately by fusion in the core, transported through the radiative zone, churned through the convective zone, and released into space. The sun is not just a light source, it's an engine, a system, a complex layered dynamic structure where each part plays a role. Now, here's something remarkable. We can't see inside the sun directly. We can't drill into it or send probes into its core. The temperatures and pressures would destroy anything we could build. So, how do we know about these layers? How do we know the radiative zone exists? How do we measure the temperature and density at different depths? The answer is helioseismology, the study of vibrations in the sun. Just like earthquakes create seismic waves that travel through Earth and tell us about its internal structure, the sun also vibrates. These vibrations are caused by turbulence in the convective zone. Sound waves propagate through the interior, bouncing off different layers, reflecting, refracting, interfering. And these waves cause the surface to move, to oscillate, to rise and fall by tiny amounts, usually just a few meters, sometimes up to a kilometer. By carefully measuring these oscillations, using instruments like the Michelson Doppler imager on the SOHO spacecraft, scientists can map the interior structure of the sun. Different vibration modes penetrate to different depths. By analyzing millions of oscillation patterns, scientists can reconstruct the temperature density and composition profile of the sun's interior with remarkable precision. It's like doing a CT scan of a star, using sound waves instead of X-rays, listening instead of looking. And what helioseismology revealed confirmed our theoretical models. The core is about 15 million Kelvin. The radiative zone extends to about 70% of the radius. The convective zone takes over after that. The predictions match the observations. It was a triumph of both theory and observation. Proof that we really do understand what's happening inside the sun, even though we can't see it directly. In the 1960s and 70s, there was actually a crisis in solar physics called the solar neutrino problem. Experiments designed to detect neutrinos from the sun were only finding about 1/3 as many as predicted by theory. Either our understanding of fusion was wrong, or something strange was happening to the neutrinos on their way to Earth. It took decades to solve, but eventually scientists realized that neutrinos were changing type, oscillating between different flavors as they traveled. This phenomenon, called neutrino oscillation, required neutrinos to have mass something not predicted by the original standard model of particle physics. The discovery of neutrino oscillation won the Nobel Prize in Physics in 2015, awarded to Takaaki Kajita and Arthur McDonald, and it confirmed that our models of the sun's core were correct after all. The neutrino deficit wasn't because we misunderstood fusion. It was because we misunderstood neutrinos. So the layers of the sun are real. They're not just theoretical constructs. They're physical regions with measurable properties confirmed by multiple lines of evidence. And every star has similar layers. The exact sizes and temperatures vary depending on the star's mass, but the basic structure is the same. Core radiative zone, convective zone, photosphere. Some stars, very low-mass red dwarfs, are fully convective. They don't have a radiative zone at all. Convection carries energy from core to surface. Other stars, very massive ones, have convective cores but radiative envelopes. The energy transport is reversed. But for stars like the Sun and many others, the layered structure is the same. Fusion in the core, radiative transport in the deep interior, convective transport near the surface, and finally escape into space. It's a system, a machine, a structure born from physics maintained by balance powered by fusion. And it's been running steadily for billions of years. Think about that for a moment. Think about the complexity, the precision, the fact that energy created in the core hundreds of thousands of years ago is just now reaching the surface, just now escaping as light. The sun is a time machine in a sense. It's still releasing energy from reactions that happened during the Stone Age. And it will continue releasing that ancient energy for ages to come. There's something profound in that, isn't there? Something that connects us to deep time, to processes we can't see but can feel, to a structure hidden beneath layers of light. But we've been talking about the sun's interior, its hidden architecture, the journey of light through darkness. Now, it's time to talk about the light itself once it escapes. Because that light carries information. It carries secrets encoded in its wavelengths, its colors, its missing pieces. And we learn to read that code. We learn to decode starlight. That's where we turn next. Light doesn't just illuminate, it speaks. Every beam carries a message written in a language older than words, a language of wavelengths and gaps of colors present and colors missing. And somehow, impossibly, we learn to read it. We learn to decode the whispers hidden in starlight, to see not just brightness, but chemistry, not just color, but temperature, not just presence, but motion. This is the story of how we learned to listen to what the stars were saying. In 1802, an English chemist named William Wollaston was studying sunlight in his laboratory. He passed a beam through a narrow slit, then through a glass prism, to split it into its component colors. This was nothing new. Isaac Newton had done similar experiments more than a century earlier, showing that white light was actually composed of all the colors of the rainbow. But Wollaston noticed something strange. When he looked closely at the spectrum, the rainbow band of colors, he saw dark lines crossing it. 7 of them thin and precise, always in the same positions. He didn't know what they meant. He mentioned them briefly in a paper and moved on. It would take another scientist to realize their significance. In 1814, a young German optician named Joseph von Fraunhofer was developing better optical glass for telescopes. He needed a way to measure the quality of his glass, so he started studying the spectrum of sunlight in extraordinary detail. And he found not 7 dark lines, but hundreds. Using instruments he built himself, including the first modern spectroscope, Fraunhofer mapped 574 distinct dark lines across the solar spectrum. He labeled the most prominent ones with letters the A line, B line, C line, all the way through the alphabet. Some of those labels are still used today. The D line, for instance, is the sodium doublet at 589 nanometers, the characteristic orange-yellow of sodium street lamps. Fraunhofer didn't know what caused these lines. He didn't know they were the fingerprints of chemical elements. But he mapped them carefully, precisely giving future scientists the data they would need to unlock their meaning. It took another 50 years. In the 1850s and 60s, scientists like Gustav Kirchhoff and Robert Bunsen, yes, the same Bunsen who invented the Bunsen burner, were studying the light emitted by heated elements. They discovered that each element, when heated, emits light at very specific wavelengths. Sodium always produces light at 589 nanometers. Hydrogen produces a series of lines in the visible spectrum, red at 656 nanometers blue-green, at 486 nanometers violet, at 434 nanometers. Each element has its own unique pattern, its own signature, its own fingerprint. And then came the crucial insight. If a continuous spectrum of light passes through a cool gas containing those elements, the gas absorbs light at precisely the same wavelengths it would emit. So you get dark lines instead of bright ones, absorption lines instead of emission lines. The pattern is reversed, but the wavelengths are the same. This explained Fraunhofer's dark lines. Sunlight, which starts as a continuous spectrum from the hot photosphere, passes through the cooler layers of the sun's atmosphere. Elements in those cooler layers absorb their characteristic wavelengths, leaving dark gaps in the spectrum. By comparing the dark lines in sunlight to the bright lines produced by heated elements in the laboratory, scientists could identify which elements were present in the sun: hydrogen, helium, iron, calcium, sodium, magnesium. Dozens of elements identified from 150 million kilometers away without ever touching the sun. It was revolutionary, miraculous almost. For the first time in history, humans could know what distant objects were made of. Chemistry, once limited to the laboratory, became cosmic. And here's something remarkable. In 1868, during a solar eclipse, French astronomer Pierre Janssen was studying the sun's chromosphere when he noticed a bright yellow line that didn't match any known element. English astronomer Norman Lockyer, independently observing the same phenomenon, also noticed this mysterious line. He proposed that it came from a new element, one that hadn't been discovered on Earth yet. He named it helium, after Helios, the Greek god of the sun. Scientists searched for helium on Earth for nearly 3 decades. It wasn't found until 1895, when Scottish chemist William Ramsay isolated it from a uranium-bearing mineral called cleveite. Think about the implications of that. We discovered an element in the sun before we found it on Earth. We identified it purely through spectroscopy, purely by reading the language of light. Helium turned out to be the second most abundant element in the universe after hydrogen. It's everywhere. But on Earth, it's relatively rare because it's so light it escapes into space. The fact that we found it in the sun first shows the power of spectroscopy. It expanded our chemistry beyond our planet. It made the universe our laboratory. Now spectroscopy doesn't just tell us what stars are made of. It tells us much more. For one thing, it tells us temperature. The overall shape of a star's spectrum, which wavelengths are brightest, which are dimmer, depends on the star's surface temperature. This relationship is described by Planck's law and Wien's displacement law. Wien's law, discovered in 1893, states that the peak wavelength of radiation is inversely proportional to temperature. Hotter objects emit more light at shorter wavelengths. Cooler objects emit more light at longer wavelengths. A very hot star with a surface temperature of 30,000 Kelvin or more appears blue because its spectrum peaks in the blue or ultraviolet part of the spectrum. A cooler star with a surface temperature of 3,000 Kelvin appears red because its spectrum peaks in the red or infrared. Our sun, at about 5,500 Kelvin, peaks in the yellow-green part of the spectrum, but emits enough light across the visible range that it appears white or slightly yellow to our eyes. So, just by looking at a star's color, or more precisely by measuring its spectrum, we can determine its surface temperature. Astronomers use this to classify stars. The standard classification system, developed in the early 20th century at Harvard College Observatory, organizes stars by temperature using the letters O, B, A, F, G, K, M. O stars are the hottest, above 30,000 Kelvin blue and fierce. M stars are the coolest, below 3,500 Kelvin red and dim. The Sun is a G-type star, specifically a G2V star where the 2 indicates a specific temperature within the G range, and the V indicates it's a main sequence star. Astronomers have a mnemonic to remember the sequence, "Oh, be a fine girl, kiss me." There are other variations, some more modern and inclusive, but the idea is the same, a memory aid for a temperature scale encoded in letters. This classification system, refined by Annie Jump Cannon and her colleagues at Harvard, became the standard used by astronomers worldwide. Cannon personally classified over 350,000 stars during her career, an astonishing feat of dedication and precision. But spectroscopy tells us even more. It tells us motion. When a star is moving toward us or away from us, the wavelengths of its light are shifted slightly due to the Doppler effect. You've experienced the Doppler effect with sound. When an ambulance approaches its siren, sounds higher pitched. As it passes and moves away, the pitch drops. The actual frequency of the siren doesn't change. What changes is the frequency you perceive because of the relative motion. Light works the same way. When a star is moving toward us, its light waves are compressed, shifted toward shorter wavelengths, toward the blue end of the spectrum. This is called blue shift. When a star is moving away from us, its light waves are stretched, shifted toward longer wavelengths, toward the red end of the spectrum. This is called red shift. By measuring how much the spectral lines are shifted from their rest wavelengths, we can calculate the star's velocity along our line of sight, approaching or receding, and how fast. This technique, called radial velocity measurement, has been crucial for astronomy. It's how we discovered that most galaxies are moving away from us, the expansion of the universe. It's how we measure the rotation of galaxies. It's how we detect exoplanets by watching for the tiny wobble they induce in their parent star. When a planet orbits a star, it doesn't orbit a fixed point. Both the planet and the star orbit their common center of mass. For a large planet, this causes the star to wobble slightly, moving toward us, then away from us in a regular pattern. The first exoplanet discovered around a Sun-like star, 51 Pegasi b, was found using this method in 1995. Michael Mayor and Didier Queloz measured the periodic Doppler shift in the star's spectrum and inferred the presence of a Jupiter-sized planet in a 4-day orbit. They shared the Nobel Prize in Physics in 2019 for this discovery. Since then, radial velocity measurements have confirmed thousands of exoplanets. The technique is precise enough to detect velocity changes of just 1 meter per second walking speed. Imagine that, measuring the motion of a star hundreds of light years away with such precision that you can detect changes equivalent to a slow walk. That's the power of spectroscopy. But let's go deeper. Let's talk about what else the spectral lines reveal. The width of spectral lines tells us about several things. Pressure broadening occurs when the gas is dense, atoms are packed close together, and their interactions slightly alter the wavelengths they emit or absorb, broadening the lines. Thermal broadening occurs because atoms are moving. In a hot gas, atoms move faster, and the Doppler effect from their random motion spreads out the spectral line. And rotation broadening occurs when a star is spinning. One edge of the star is moving toward us, the other away from us, and this causes the spectral lines to broaden. By analyzing the exact shape and width of spectral lines, astronomers can determine a star's density, temperature, rotation, speed, even the strength of its magnetic field. Every detail carries information. Every feature is a clue. It's like forensic science for the universe. We can't touch the stars, can't sample them directly, but we can analyze their light with such precision that we know them intimately anyway. Now, here's something most people don't realize. Spectroscopy also tells us about what's between us and the star. If light from a distant star passes through a cloud of gas on its way to Earth, that gas will imprint its own absorption lines on the spectrum. This is how we discovered the interstellar medium, the thin gas and dust between stars. We saw absorption lines that couldn't be coming from the stars themselves. They had to be coming from material in the space between. In the early 20th century, astronomers noticed mysterious absorption lines in the spectra of some stars. Lines that didn't match any known element. Lines that seemed to appear and disappear depending on the star's location in the sky. They called these interstellar lines, and by studying them, they mapped the distribution of gas clouds throughout the galaxy. One particularly interesting discovery came in 1937. Astronomer Paul Swings identified absorption lines from simple molecules CN, CH, CH+, in the interstellar medium. These were the first molecules detected in space. At the time, many scientists thought space was too harsh for molecules to survive. The radiation, the vacuum, the cold. Molecules should be torn apart, shouldn't they? But there they were, recorded in Starlight. Carbon monoxide, hydrogen molecules, water vapor, even more complex organic molecules. Spectroscopy revealed that space is not empty. It's full of chemistry, full of the raw materials for stars and planets and eventually life. Fast forward to today, and we've detected over 200 different molecules in space. Some of them are surprisingly complex. Amino acids, sugars, alcohols, polycyclic aromatic hydrocarbons, all detected through spectroscopy, all found by reading the language of light. There's a certain poetry to it, isn't there? That light in its journey across space picks up stories. It absorbs and emits. It interacts and records. And when it finally reaches us, it's carrying a message written in wavelengths. We just had to learn the language, and we did. Slowly, painstakingly, over more than a century, we decoded the spectrum. We learned what each line means, what each gap reveals. Now let me tell you about a common misconception. Many people think that when we say we've detected an element in a star, we're somehow seeing that element directly, that we're looking at it through a telescope. But that's not quite right. We're not seeing the elements, we're seeing their effects on light. We're reading the evidence they leave behind. It's like detective work. You don't need to see the criminal to know they were there. Fingerprints, footprints, DNA. These are enough. They tell the story. Spectral lines are the fingerprints of elements. And they're just as reliable, just as definitive. In fact, spectroscopy is so precise that we can not only identify elements, but determine their isotopes, different versions of the same element, with different numbers of neutrons. Normal hydrogen has 1 proton, no neutrons. Deuterium, heavy hydrogen, has 1 proton and 1 neutron. The spectral lines are almost identical, but shifted slightly because the atom is heavier. By measuring that tiny shift, we can determine the ratio of hydrogen to deuterium in a star or an interstellar gas or in a planet's atmosphere. This ratio tells us about the history of that material, where it came from, what processes it went through. Spectroscopy doesn't just tell us what's there, it tells us the story of how it got there. And here's something beautiful. Spectroscopy works across all wavelengths, not just visible light. Radio spectroscopy detects the 21-centimeter line from neutral hydrogen, allowing us to map the distribution of hydrogen throughout galaxies. Infrared spectroscopy detects molecules and dust, revealing star-forming regions hidden behind clouds of gas. X-ray spectroscopy detects highly ionized elements in extremely hot environments, supernova remnants, accretion disks around black holes, the hot gas between galaxy clusters. Each wavelength range reveals different aspects of the universe. Each one speaks a different dialect of light's language, and we've learned to listen to all of them. Modern telescopes are equipped with sophisticated spectrographs, instruments that split light into its component wavelengths with incredible precision. Some can distinguish wavelengths that differ by less than 1 part in 100,000. That's like being able to distinguish between 2 musical notes that differ by less than 1,000th of a semitone. Precision beyond human hearing applied to light. With that precision, we can measure the expansion of the universe. We can detect the wobble of distant stars caused by orbiting planets. We can map the chemical composition of galaxies billions of light years away. We can, in essence, do chemistry across the cosmos. We can analyze what stars are made of, what planets are made of, what galaxies are made of, all from here on Earth. It's one of humanity's greatest intellectual achievements, right up there with language mathematics, the scientific method itself. Because spectroscopy is how we escaped our provincial ignorance, how we stopped being limited to the chemistry of our own planet and started understanding the chemistry of everything. Joseph von Fraunhofer, mapping those dark lines in 1814, probably never imagined where it would lead. That his careful measurements would become the foundation for understanding the composition of stars, the motion of galaxies, the expansion of the universe itself. He was just trying to make better glass, trying to improve telescopes, and in doing so, he gave us the key to decoding starlight. That's how science works sometimes. You're solving one problem and you stumble into something vast, something that changes everything. The dark lines in sunlight seemed like a curiosity, a minor puzzle, but they were actually the alphabet of a language spoken by every star, every galaxy, every glowing object in the universe. And once we learned that language, once we understood what those lines meant, we could never see the stars the same way again. They weren't just points of light anymore. They were sources of information, libraries, archives containing billions of years of cosmic history waiting to be read. All we had to do was listen, and we did. We continue to. With better instruments, deeper understanding, more questions to ask. Because every answer in science opens up new questions. Every mystery solved reveals deeper mysteries. And the stars keep speaking. Keep broadcasting their secrets into space encoded in light, waiting for anyone curious enough to listen. But there's another secret hidden in starlight, one we haven't touched on yet. A secret not just about what stars are made of, but about how hot they are, how they differ from each other, why some burn blue while others glow red. That story, that spectrum of temperature and color, that's where we're heading next. Look up at the night sky on a clear evening, and you might notice something subtle. Not all stars are the same color. Some shine white bright and sharp. Others glow with a faint reddish tint. A few, if you look carefully, have a blue-white brilliance that stands out among the rest. Most people assume stars are all the same, just different brightnesses. But that's not true. Stars come in colors, and those colors, they're not random. They're not decoration. They're thermometers. Messages written in temperature, stories told in heat. Let's learn to read them. In the winter sky of the northern hemisphere, there's a constellation most people recognize, Orion the Hunter. And in Orion, there are two particularly bright stars that couldn't be more different. On the upper left shoulder, there's Betelgeuse. It glows with a deep orange-red color, especially noticeable through binoculars or a small telescope. It's cool by stellar standards, about 3,500 Kelvin at its surface. On the lower right, marking Orion's foot, there's Rigel. It shines with an intense blue-white light. It's scorching about 11,000 Kelvin at its surface. Same constellation, same apparent brightness roughly, but completely different temperatures, completely different colors. Why? The answer lies in a principle of physics discovered in the late 19th century by a German physicist named Wilhelm Wien. Wien was studying black-body radiation, the light emitted by objects based solely on their temperature. A black body is an idealized object that absorbs all radiation that hits it and emits radiation based purely on its temperature. No real object is a perfect black body, but stars come close. They're hot, dense, and opaque enough that their radiation is determined primarily by temperature. Wien discovered a simple relationship. The wavelength at which an object emits the most light is inversely proportional to its temperature. Hot objects emit more light at short wavelengths, blue and ultraviolet. Cool objects emit more light at long wavelengths, red and infrared. This relationship is now called Wien's displacement law. and it can be written as a simple equation: lambda max equals 2.9 million divided by temperature in Kelvin, where lambda max is the peak wavelength in nanometers. Let's apply this to stars. A very hot star with a surface temperature of 30,000 Kelvin emits most of its light at about 97 nanometers in the ultraviolet beyond what our eyes can see. But it also emits plenty of visible light, and because it's emitting more at the blue end of the visible spectrum than the red end, it appears blue to our eyes. A cool star with a surface temperature of 3,000 Kelvin emits most of its light at about 970 nanometers in the near infrared, again beyond what we can see. But the visible light it does emit is skewed toward the red end, so it appears red or orange. Our sun, at 5,500 Kelvin, emits most of its light at about 530 nanometers in the green part of the spectrum. But it emits across all visible wavelengths fairly evenly, so it appears white or slightly yellow. This is why color and temperature are connected. It's not arbitrary, it's physics. Wien's law playing out across the cosmos. And here's something interesting. The color you see isn't always the color the star actually is. What do I mean by that? Well, if a star is very hot, say 40,000 Kelvin, it's emitting most of its light in the ultraviolet. Our eyes can't see ultraviolet, so what we perceive is the visible light that spills over from the UV peak. And that visible light is mostly blue. But the star isn't really blue in the sense that blue is its brightest color. It's brightest in the ultraviolet. We're just seeing the tail end of its spectrum, the part our biology allows us to detect. Similarly, very cool stars emit most of their light in the infrared. We're seeing the visible edge of an infrared peak. So, color is perception filtered through the limits of human vision. But it's still a reliable indicator of temperature, just with the understanding that what we see is a slice of a larger reality. Now, astronomers don't classify stars just by color alone. They use the spectroscopic classification system we mentioned earlier, OBAFGKM. But this system is fundamentally based on temperature. O stars are the hottest above 30,000 Kelvin. They appear blue-white. B stars are slightly cooler around 10,000 to 30,000 Kelvin, still blue but less intensely. A stars are around 7,500 to 10,000 Kelvin, white with a hint of blue. F stars are around 6,000 to 7,500 Kelvin, white to yellow-white. G stars like our sun are around 5,200 to 6,000 Kelvin, yellow to white. K stars are around 3,700 to 5,200 Kelvin, orange. M stars are the coolest, below 3,700 Kelvin, red to deep orange. Each class is further subdivided into 10 subclasses numbered 0 through 9. The sun is a G2, meaning it's near the hotter end of the G range. This classification system was developed at Harvard College Observatory in the early 20th century by a team of women known as the Harvard Computers. They analyzed thousands of stellar spectra, classifying stars based on the patterns of absorption lines they observed. Initially, the system was based on the strength of hydrogen lines, with A stars showing the strongest hydrogen absorption. But later, astronomers realized the sequence actually represented a temperature scale. They rearranged the letters to go from hottest to coolest, O, B, A, F, G, K, M. The original letters didn't make sense in the new order, but they kept them for historical continuity. Hence the strange sequence we use today. And the woman who did most of this classification, work Annie Jump Cannon. She personally classified more than 350,000 stars over her career, creating a catalog that became the foundation of modern stellar astronomy. She could classify 3 stars per minute at her peak. Think about that. Looking at a spectrum, identifying the patterns, assigning a classification, moving to the next one. 3 per minute, hour after hour, day after day, year after year. Her work gave us the framework we still use to understand stellar populations. Now, let's talk about a common misconception. Many people think red stars are hot, and blue stars are cool. After all, we talk about red-hot metal and blue flames are less common in everyday experience. But in astronomy, it's the opposite. Blue stars are hot. Red stars are cool. Why the confusion? It comes from incomplete experiences with temperature in daily life. When you heat metal, it glows red first, then orange, then yellow, then white. We rarely see it go blue because we don't usually heat things that hot. But if you could heat metal to 10,000 Kelvin or more, it would glow blue. Blue flames in a gas stove or Bunsen burner are hotter than yellow flames. Blue stars in the sky are hotter than red stars. It's the same principle. Temperature determines color. Always. So, when you see Betelgeuse glowing red, you're seeing a star that's relatively cool. And when you see Rigel shining blue-white, you're seeing a star that's blazingly hot. Relatively cool for Betelgeuse still means 3,500 Kelvin, hot enough to vaporize any material we know. But cool compared to Rigel's 11,000 Kelvin. Everything is relative in astronomy. Now, let's talk about how we use this color-temperature relationship to measure distances. In the early 20th century, a woman named Henrietta Swan Leavitt was working at Harvard College Observatory, analyzing photographic plates of stars in the Small Magellanic Cloud, a small satellite galaxy near our Milky Way. She was studying variable stars, stars whose brightness changes over time. Specifically, she was looking at Cepheid variable stars that pulsate growing brighter and dimmer in a regular cycle. And she noticed something remarkable. The longer the period of pulsation, the brighter the star. A Cepheid that pulsed every 10 days was intrinsically brighter than one that pulsed every 3 days. The relationship was consistent, predictable. This is now called the period luminosity relationship. And it's one of the most important discoveries in astronomy. Why? Because it gives us a distance ladder. If you know a star's intrinsic brightness, how bright it actually is, and you measure how bright it appears from Earth, you can calculate its distance. Brightness decreases with the square of distance. It's a simple geometric relationship. The problem is, how do you know a star's intrinsic brightness? Leavitt's discovery gave us away. If you observe a Cepheid variable measure its period, you know its intrinsic brightness. Compare that to its apparent brightness, and you can calculate the distance. Cepheid variables became cosmic yardsticks. We could measure distances not just within our galaxy, but to other galaxies entirely. In the 1920s, Edwin Hubble used Cepheid variables to measure the distance to the Andromeda galaxy. He proved definitively that Andromeda was far outside our Milky Way, a separate galaxy in its own right. This settled a major debate in astronomy. Before Hubble's measurements, some astronomers thought Andromeda and other spiral nebulae were just gas clouds within our galaxy. Hubble showed they were entire galaxies millions of light years away. The universe suddenly got much, much bigger. And it all started with Henrietta Leavitt carefully measuring the brightness and periods of variable stars on photographic plates night after night, in an era when women weren't even allowed to operate telescopes. She wasn't looking for a distance scale. She was just cataloging stars doing the work assigned to her. But she discovered a pattern, and that pattern changed everything. That's the thing about astronomy. Sometimes the most important discoveries come from careful, patient observation, from noticing a pattern that shouldn't be there, or a regularity where none was expected. Leavitt died in 1921, before the full importance of her discovery was recognized. She never won a Nobel Prize. They're not awarded posthumously. But her work made possible some of the most fundamental discoveries in 20th century astronomy. Now, let's connect color and distance in another way. When we observe very distant galaxies, we notice something strange. Their light is shifted toward the red end of the spectrum. This is called cosmological redshift, and it's different from the Doppler redshift we talked about earlier. Cosmological redshift happens because the universe is expanding. As light travels through space, space itself is stretching, and that stretches the wavelengths of the light. The farther the galaxy, the more space the light has crossed, the more stretching has occurred, the greater the redshift. By measuring the redshift, we can determine how far away a galaxy is. And by comparing redshift measurements to brightness measurements, we can map the expansion of the universe. This is how we discovered that the universe's expansion is accelerating, that there's something called dark energy pushing everything apart faster and faster. And it all comes back to color, to wavelength, to the way temperature and motion and cosmic expansion all leave their marks on light. Color is information, always. Here's another way we use stellar colors to estimate the age of star clusters. When a cluster of stars forms, they all form at roughly the same time from the same cloud of gas. But they have different masses, and different masses age at different rates. Massive blue stars burn through their fuel quickly a few million years. Lower mass yellow stars like the Sun burn for billions of years. Low mass red dwarfs burn for trillions of years. So, if you look at a star cluster and map out which stars are still on the main sequence and which have evolved off it, you can estimate the cluster's age. If there are still blue O and B stars, the cluster is young less than 10 million years old. If the bluest stars are A or F type, it's older maybe 100 million to a billion years. If only K and M dwarfs remain on the main sequence, the cluster is ancient many billions of years old. Color becomes a clock, a way to read time, written in the evolution of stars. The Pleiades, that beautiful little cluster, visible in the winter sky, still has bright blue stars. It's young only about 100 million years old. Omega Centauri, a massive globular cluster, visible from the southern hemisphere, has no blue main sequence stars left. Only red and yellow ones. It's ancient, around 12 billion years old, almost as old as the universe itself. Same principle, different ages, all revealed by color. Now, let me tell you about one of the most famous diagrams in astronomy. In the early 20th century, Danish astronomer Einar Hertzsprung and American astronomer Henry Norris Russell independently discovered that if you plot stars on a graph with temperature on one axis and brightness on the other, they don't scatter randomly. They form patterns, structures. Most stars fall along a diagonal band called the main sequence. Some cluster in an area called the red giant branch. Others fall into a region called the white dwarf zone. This graph is now called the Hertzsprung-Russell diagram, or HR diagram, and it's one of the most important tools in stellar astronomy. The main sequence is where stars spend most of their lives fusing hydrogen into helium in their cores. Our Sun is on the main sequence. So is Proxima Centauri, the closest star to us. So are most of the stars you can see in the night sky. The position on the main sequence depends on mass. High-mass stars are at the top, left hot blue and luminous. Low-mass stars are at the bottom, right cool, red, and dim. The Sun sits comfortably in the middle. Not the hottest, not the coolest. Not the brightest, not the dimmest. Just average, unremarkable. One star among hundreds of billions. But off the main sequence, things get interesting. Red giants are stars that have exhausted the hydrogen in their cores and have started fusing helium. They've expanded enormously, hundreds of times their original size, and cooled at the surface, turning red. Betelgeuse is a red giant. So is Arcturus in the constellation Boötes. These are stars in the late stages of their lives, bloated and dim at the surface, but still producing enormous amounts of energy. White dwarfs are the remnants of stars that have exhausted all their fuel. They've shed their outer layers and left behind a hot, dense core, roughly Earth-sized, but with about half the mass of the Sun. They glow white-hot from residual heat, slowly cooling over billions of years. Sirius B, the companion to Sirius. The brightest star in the night sky is a white dwarf. It was discovered in 1862 by telescope maker Alvin Graham Clark while he was testing a new telescope. The discovery of Sirius B was remarkable because it confirmed a prediction made by Friedrich Bessel in 1844. Bessel noticed that Sirius was wobbling slightly in its path across the sky, as if something was tugging on it. He predicted an unseen companion. 18 years later, Clark saw it, a faint point of light next to brilliant Sirius, the first white dwarf ever observed. And when astronomers analyzed its spectrum, they were shocked. It was hot about 25,000 Kelvin, but incredibly dim for that temperature. The only explanation was that it was tiny, dense beyond comprehension. We now know that a white dwarf packs about half the sun's mass into a sphere the size of Earth. A teaspoon of white dwarf material would weigh about 15 tons. The HR diagram shows us all of this. It maps the life cycle of stars. It shows us where stars are born, how they age, where they end. And it's all based on two things: color and brightness, temperature and luminosity, two measurements, two pieces of information, and from them, we can reconstruct an entire stellar biography. That's the power of systematic observation, of careful measurement, of finding the patterns hidden in the data. So, when you look at the stars tonight, try to see their colors. Notice that Arcturus is orange, that Vega is white, that Antares is red, that Spica, it's blue-white. Each color is a temperature. Each temperature tells a story of fusion rates, lifetimes, evolutionary stages. Blue stars are burning fast, living bright and short. Red stars are smoldering slow, patient, enduring. And between them all the colors of the stellar rainbow, each one a chapter in the book of cosmic time. But color is just the beginning. Because stars don't just shine steadily for billions of years and then wink out. They change, they evolve, they pass through stages, each one dramatic, each one transformative. And some of those changes, they're violent, spectacular, universe-altering. That's the journey we're about to take. Stars are not eternal. They're born, they live, they change, and eventually they die. But death for a star is not quiet. It's not gentle. For some, it's the most spectacular event in the universe, an explosion so bright it can outshine an entire galaxy for weeks. And in that death, that violent, catastrophic end, they give birth to everything that makes life possible. Every atom heavier than helium in your body was forged in the dying moments of a star, or in the collision of stellar corpses, or in the furnace of a supernova. Let's walk through that journey, from stability to transformation to the final brilliant goodbye. For most of a star's life, it's stable, balanced. We call this phase the main sequence, and it's where stars spend about 90% of their existence. During the main sequence, a star is fusing hydrogen into helium in its core. The energy release creates outward pressure that balances gravity's inward pull. Everything is in equilibrium. Nothing changes, not really not, for billions of years. Our sun has been on the main sequence for about 4.6 billion years. It will remain there for another 5 billion or so. 10 billion years total of stable, steady shining. That's a long time. Longer than life has existed on Earth. Longer than Earth itself has existed in its current form. But nothing lasts forever. Not even stars. Eventually, the hydrogen in the core runs out. It's been fusing for billions of years, slowly converting hydrogen to helium, and eventually there's no hydrogen left. Just helium. Inert helium that won't fuse under the current conditions. And when the fusion stops, the pressure stops. The balance breaks. Gravity wins. The core begins to contract. As it contracts, it heats up gravitational energy, converting to thermal energy, just like it did when the star first formed. But now, something different happens. The contracting core heats the surrounding shell of hydrogen that wasn't part of the core. That hydrogen starts fusing, so now you have a shell of fusion surrounding an inert helium core. This shell fusion is more energetic than core fusion was. It produces more energy, and that energy pushes the outer layers of the star outward. The star expands enormously, hundreds of times its original size. But as it expands, its surface cools. Hot things spread thin become cooler. The star's surface temperature drops from maybe 6,000 Kelvin to 3,000 or 4,000 Kelvin. it turns red. This is the red giant phase, and every sun-like star will go through it eventually. Our sun, about 5 billion years from now, will swell into a red giant. It will expand past the orbit of Mercury, past Venus. It might even reach Earth's orbit, though Earth will likely have spiraled outwards somewhat due to the sun losing mass. But even if Earth isn't engulfed, it will be sterilized. The oceans will boil away. The atmosphere will be stripped. The surface will become molten rock glowing faintly in the harsh light of a dying sun. Life on Earth, if it still exists, will need to have migrated elsewhere long before that happens. It's a sobering thought, isn't it? That the sun, so constant, so reliable, so essential to everything we know, has an expiration date. A time when it will cease to be the gentle warmth that nurtured life and become instead an expanding, dying monster. But that's billions of years away. For now, the sun is stable, safe, nurturing. Let's continue the story. As the red giant phase progresses, the helium core keeps contracting and heating. Eventually, it reaches about 100 million Kelvin. At that temperature, helium nuclei can fuse. 3 helium nuclei combine to form carbon through a process called the triple alpha process. It's called that because helium nuclei are also known as alpha particles, and you need 3 of them. Sometimes a 4th helium nucleus fuses with the carbon, creating oxygen. So now the star is fusing helium into carbon and oxygen in its core, with a shell of hydrogen fusion above it. It's a layered structure, an onion of fusion reactions. This phase is shorter than the main sequence, much shorter. For a sun-like star, the helium fusion phase lasts only about 100 million years compared to 10 billion years on the main sequence. The higher up the fusion chain you go, the shorter the phases become. Hydrogen fusion lasts billions of years. Helium fusion lasts hundreds of millions. Carbon fusion for stars massive enough to achieve it lasts thousands of years. Silicon fusion. The final stage for massive stars lasts only days. The star is running out of time, burning faster and faster, approaching an end. For stars like the sun, stars below about 8 solar masses, the story ends relatively gently. When the helium runs out, the core contracts again, but it never gets hot enough to fuse carbon. The star doesn't have enough mass, enough gravitational squeeze to reach the temperatures needed. Instead, the outer layers puff off into space, forming what's called a planetary nebula. The name is misleading. It has nothing to do with planets. Early astronomers seeing these glowing shells through primitive telescopes thought they looked like planets. The name stuck. The Ring Nebula in Lyra is a planetary nebula. So is the Cat's Eye Nebula. So is the Helix Nebula, sometimes called the Eye of God because of its appearance. These are the outer layers of dead stars glowing in the light of the hot core left behind. And that core, that tiny, dense remnant, that's a white dwarf. It's about the size of Earth, but contains about half the sun's mass. The density is extraordinary. A teaspoon of white dwarf material would weigh about 15 tons on Earth. And it's supported not by fusion, there's no fusion happening anymore, but by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed too close together. The white dwarf just sits there, slowly cooling, slowly fading over trillions of years. Eventually, it will become a black dwarf, a cold, dark cinder floating in space. But the universe isn't old enough yet for any black dwarfs to exist. Even the oldest white dwarfs are still glowing faintly. This is the fate of the sun. This is the end of most stars in the galaxy. Not dramatic, not violent, just a slow fading into darkness. But for more massive stars, stars above about 8 solar masses, the story is very different. These stars have enough mass that when the core contracts after helium fusion, it does get hot enough to fuse carbon. Carbon fuses into neon, magnesium, oxygen. Those fuse into silicon and sulfur. Silicon fuses into iron. Each stage happens faster than the last. The star is racing through its nuclear fuel, desperate to keep gravity at bay, burning through elements at an accelerating pace. Carbon fusion, 1,000 years. Neon fusion, a few years. Oxygen fusion, months. Silicon fusion, days. And then, iron. Iron is the end of the line. Iron 56 is the most stable nucleus. It has the highest binding energy per nucleon of any element. Fusing iron doesn't release energy, it costs energy. If the core tries to fuse iron, it actually cools down instead of heating up. So when the core becomes iron, fusion stops. Suddenly. Completely. And with no fusion, there's no pressure to hold the star up. Gravity wins, catastrophically. The core collapses. In less than a second, an iron core the size of Earth collapses to a sphere only about 20 kilometers across. The density becomes so extreme that protons and electrons are forced together, forming neutrons and releasing neutrinos. You now have a neutron star, a sphere of pure neutrons packed so tightly that a sugar cube-sized piece would weigh about 1 billion tons. But the collapse doesn't stop smoothly. When the core reaches nuclear density, it suddenly becomes incompressible. The infalling matter bounces. It rebounds outward with tremendous force. This creates a shock wave, a blast wave traveling outward through the star at about 10% the speed of light. And as it travels, it heats the layers above, triggering explosive fusion reactions. Elements heavier than iron, gold, platinum, uranium are created in these few seconds of extreme conditions. The outer layers of the star are blown into space at thousands of kilometers per second. The explosion releases more energy in a few weeks than the star released during its entire lifetime. This is a supernova, and for a brief time, days to weeks, a single supernova can outshine an entire galaxy of hundreds of billions of stars. It's one of the most energetic events in the universe, short of the Big Bang itself, and perhaps the collision of black holes. The most famous supernova in modern history is SN 1987A, observed on February 23, 1987. It occurred in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, about 168,000 light-years away. Astronomers around the world watched it brighten, peak, and slowly fade over months and years. It was visible to the naked eye from the southern hemisphere, the first naked-eye supernova since 1604. And here's something remarkable: neutrino detectors on Earth caught the neutrino burst from SN 1987A hours before the light arrived. The neutrinos escaped from the collapsing core immediately, while the light had to fight its way out through the exploding star. 25 neutrinos were detected by various detectors around the world. Out of the 10^58 neutrinos released by the supernova, Earth caught 25. That's how rare neutrino interactions are. And yet those 25 detections confirmed our theories about core collapse. They proved we understood what was happening in the heart of a dying star. Now, not all massive stars become neutron stars. For the most massive stars above, about 25 solar masses, the core collapse is so extreme that even neutron degeneracy pressure can't stop it. The core keeps collapsing, past the neutron star phase, past any known mechanism to halt it. It collapses into a black hole, a region of space-time so warped that nothing, not even light, can escape. A singularity surrounded by an event horizon. The outer layers still explode as a supernova, but the core vanishes from the universe as we know it. It becomes something else, something that physics can describe mathematically, but struggles to comprehend conceptually. Supernovae are crucial to the universe. Without them, there would be no heavy elements, no carbon for organic chemistry, no oxygen for water and respiration, no iron for blood, no calcium for bones, no silicon for rocks and electronics. Everything heavier than helium, up to about iron, is made in stars during their normal lifetimes. But everything heavier than iron, including about half the elements lighter than iron, is made in supernovae. You are made of supernova debris. The atoms in your body are the ashes of dead stars. Carl Sagan said it best: "We are made of star stuff." But more specifically, we're made of supernova stuff. We're the children of stellar catastrophe. And here's something beautiful. When a supernova explodes, it sends a shockwave through the surrounding interstellar medium. That shockwave compresses nearby gas clouds, and compressed gas clouds can collapse to form new stars. So the death of one star triggers the birth of others. It's a cycle. Death feeding birth. Endings creating beginnings. Our sun, our solar system probably formed in a region that was compressed by a nearby supernova shockwave billions of years ago. The shock that killed some ancient massive star may have been the trigger that birthed our world. There's a poetic symmetry to it, the universe recycling itself. Nothing wasted, nothing truly lost, just transformed. But supernovae aren't the only way massive stars die. There's another path even more violent, even more energetic. Sometimes two neutron stars orbiting each other in a binary system slowly spiral inward. They're losing energy to gravitational waves ripples in space-time, predicted by Einstein and detected for the first time in 2015. Eventually, they collide. And when they do, they release more energy in a fraction of a second than the sun will release in its entire 10 billion year lifetime. The collision produces a kilonova similar to a supernova, but powered by radioactive decay of heavy elements rather than core collapse. And in the extreme conditions of the collision, elements heavier than iron are forged in abundance. Gold, platinum, uranium, much of it comes from neutron star collisions. The gold in jewelry, the platinum in catalytic converters, the uranium in nuclear reactors, all of it was made in the violent merger of stellar corpses. In August 2017, gravitational wave detectors and telescopes around the world observed a neutron star collision in a galaxy 130 million light-years away. It was designated GW1-70817, and it was a watershed moment in astronomy. For the first time, we detected an event in both gravitational waves and light. We saw the space-time ripples and the electromagnetic radiation. We confirmed that neutron star collisions produce heavy elements. We measured the expansion rate of the universe using a completely new method, one event, multiple breakthroughs. That's the power of modern multi-messenger astronomy. Now, let's talk about what happens to the remnants. Planetary nebulae, the shells puffed off by dying sun-like stars, expand into space, enriching the interstellar medium with carbon, nitrogen, oxygen. They glow for tens of thousands of years before dispersing completely. Supernova remnants expand for hundreds of thousands of years. The Crab Nebula remnant of a supernova observed by Chinese and Arab astronomers in 1054 CE is still expanding. It's now about 11 light-years across and growing at about 1,500 kilometers per second. At the center of the Crab Nebula is a pulsar, a rapidly spinning neutron star emitting beams of radiation like a cosmic lighthouse. We'll talk more about pulsars soon, but the important point is, this stellar death is not sterile. It's not a clean removal of matter from the universe. It's messy, explosive, enriching. Every star that dies returns its material to space, where it can be incorporated into new stars, new planets, new life. The iron in your blood was forged in a supernova. The calcium in your bones was made in the final moments of a dying star. The oxygen you breathe was created in a red giant's helium-burning shell. You are recycled stardust, built from the ashes of multiple generations of stars that lived and died before the sun was born. And when the sun dies billions of years from now, it will return its material to space. The carbon and oxygen in its core will drift through the galaxy. And maybe some of those atoms will end up in a new star, a new planet, a new form of life that looks up at its sky and wonders where it came from. The cycle continues, always has, always will. As long as there are stars, as long as there's time, the universe will keep building and destroying and rebuilding. Stars are temporary, but what they create, that's eternal. Passed from generation to generation, recycled, endlessly transformed, but never lost. It's a comforting thought in a way, that nothing truly ends. It just changes form, becomes something else, something new. But some stellar remnants don't fade quietly. Some keep shining, kept spinning, beaming, pulsing, with a regularity that seems almost impossible. These are the lighthouses of the cosmos, the timekeepers of the universe, the strange and wonderful objects we call pulsars. And they're stranger than almost anything else we've discovered. Imagine a sphere the size of a city. Imagine it contains more mass than the sun. Imagine it spinning. Not slowly, not like Earth turning once per day, but hundreds of times per second. So fast that a point on its equator is moving at a significant fraction of the speed of light. And imagine it's beaming radiation into space like a lighthouse sweeping the cosmos with pulses so regular you could set a clock by them. These objects exist. They're called pulsars. And they're among the strangest, most extreme objects in the universe. They're the lighthouses at the edge of physics, the timekeepers of the cosmos, the remnants of catastrophe spinning in the dark. Let's listen to what they're saying. On November 28, 1967, a 24-year-old graduate student named Jocelyn Bell was analyzing data from a radio telescope at Cambridge University. She was studying quasars' distant energetic galaxies, and she noticed something odd in the data, a bit of scruff, as she called it. A regular pattern of pulses appearing once every 1.3 third of 3 seconds. At first, she thought it might be interference. Maybe a car passing by, maybe electrical equipment. Radio telescopes pick up all sorts of noise, but the signal kept appearing, same period, same strength, and it was coming from a fixed point in the sky. As Earth rotated, the signal rose and set with the stars, proving it was astronomical in origin. She showed it to her supervisor, Anthony Hewish. Together, they ruled out terrestrial sources. They considered the possibility of aliens. Half-jokingly, they called the signal LGM-1 for Little Green Men. But Bell kept searching, and she found another pulsing source, then another. 4 in total, all from different directions in the sky. Aliens seemed unlikely to be broadcasting from multiple locations with different pulse rates. It had to be a natural phenomenon. But what the answer when it came was almost as strange as aliens would have been. These were neutron stars, the collapsed cores of massive stars after supernova explosions. Objects predicted theoretically, but never observed. Objects so dense that a teaspoon of their material would weigh 1 billion tons on Earth, and they were spinning, rapidly, beaming radiation like cosmic lighthouses. The discovery was revolutionary. It confirmed the existence of neutron stars and opened a new window on extreme physics. In 1974, Anthony Hewish was awarded the Nobel Prize in Physics for the discovery. Jocelyn Bell was not included, despite having made the initial observation and doing much of the analysis. This omission remains controversial in the history of science, a reminder that recognition doesn't always go where it's deserved. Bell herself has been gracious about it, but many physicists believe she should have shared the prize. She discovered pulsars. The Nobel Committee honored the wrong person. Regardless, the discovery changed astronomy. It gave us pulsars, and pulsars are extraordinary. Let's understand what they are and how they work. When a massive star's core collapses during a supernova, protons and electrons are crushed together so tightly that they merge, forming neutrons. What you're left with is essentially a giant atomic nucleus, pure neutrons packed to nuclear density. A neutron star is typically about 20 kilometers in diameter. Manhattan is about 20 kilometers long. That's the scale. A stellar core compressed to the size of a city. But it contains about 1.4 times the sun's mass. All that mass in a sphere you could drive across in 20 minutes if there were roads. The density is incomprehensible. A sugar cube-sized chunk of neutron star matter would weigh about 1 billion tons. Drop it on Earth and it would punch through the planet like it wasn't there. And they spin. Fast. When the core collapses, conservation of angular momentum speeds up the rotation dramatically. Just like a figure skater spinning faster when they pull their arms and a collapsing star spins faster as it shrinks. A star that was rotating once per month might after collapse rotate hundreds of times per second. The fastest known pulsar PSR, J174824446AD, spins 716 times per second. That's 716 rotations in the time it takes you to say, 1 Mississippi. At that rate, a point on the pulsar's equator is moving at about 24% the speed of light. Any faster and centrifugal force would tear the star apart. It's rotating at the edge of what's physically possible for an object held together by gravity. Now, here's where the pulse comes from. Neutron stars have powerful magnetic fields. When the core collapses, the star's magnetic field is compressed along with everything else. The field strength increases by a factor of trillions. A typical neutron star might have a magnetic field strength of 10^8 to 10^12 Tesla. For comparison, Earth's magnetic field is about 0.005 Tesla. A strong MRI machine is about 3 Tesla. Neutron star magnetic fields are billions of times stronger. These intense magnetic fields channel charged particles from the neutron star's surface along the magnetic poles. As these particles spiral along the field lines, they emit radiation, radio waves, X-rays, sometimes even gamma rays. But here's the key. The magnetic poles don't align with the rotation axis. Just like Earth's magnetic North Pole isn't exactly at the geographic North Pole, a neutron star's magnetic poles are tilted. So as the neutron star spins, the beams of radiation sweep around like a lighthouse. If one of those beams happens to point toward Earth, we see a pulse. Then the beam sweeps away, and we see nothing. Then it comes around again, and we see another pulse. The pulsar isn't actually pulsing, it's beaming continuously. We just see the beam once per rotation. This is called the lighthouse effect, and it's crucial to understanding pulsars. It also means we only detect pulsars if their beams happen to point at us. Most neutron stars probably aren't pulsars. From our perspective, their beams miss Earth entirely. We're only seeing the ones that are aimed our way by cosmic chance. Scientists estimate there are about 100 million neutron stars in our galaxy. We've detected only about 3,000 solars as pulsars. The rest are invisible to us, spinning silently in the dark. Now here's something remarkable about pulsar timing. Pulsars are extraordinarily regular. The most stable ones keep time better than atomic clocks. Their pulses arrive with such predictability that astronomers can use them as cosmic clocks. The pulsar PSR B1T937+21, discovered in 1982, was for many years the most stable clock known to science. Its period is 1.5578 milliseconds, and it varies by less than a few nanoseconds per year. That's more stable than the Earth's rotation, more stable than the orbit of planets. For a while, pulsars were the most accurate timekeepers in the universe. Only in recent decades have our atomic clocks become more precise than the best pulsars, and even then it's close. This stability is useful. By timing pulsars precisely, astronomers can detect tiny changes in their rotation, and those changes reveal physics. When pulsars slow down slightly, which they all do gradually as they lose energy, we can measure that slowdown. It tells us how much energy they're radiating, how strong their magnetic fields are, how old they are. Some pulsars are in binary systems, orbiting another star or another neutron star. The orbit affects the timing of pulses through general relativistic effects. Time dilation, gravitational redshift, changes in path length as the pulsar moves toward and away from us. By analyzing these timing variations, astronomers can test Einstein's theory of general relativity with extraordinary precision. In 1974, astronomers Russell Hulse and Joseph Taylor discovered a binary system containing 2 neutron stars orbiting each other. It's called the Hulse-Taylor binary, or PSR B1913+16. By carefully timing the pulses over many years, they measured the orbital decay the two neutron stars were slowly spiraling inward, losing energy. And the rate of energy loss matched exactly what Einstein's theory predicted for gravitational wave emission. The two neutron stars were radiating gravitational waves, ripples in space-time, carrying energy away from the system. The orbit was decaying at precisely the rate predicted by general relativity. This was the first indirect evidence for gravitational waves 4 decades before they were detected directly. Hulse and Taylor won the Nobel Prize in Physics in 1993 for this work. The Hulse-Taylor binary is still being monitored. The two neutron stars will eventually collide in about 300 million years, producing a kilonova and likely a black hole. But we've already learned an enormous amount from watching them dance. Now, not all pulsars are the same. There are different types each with unique properties. Most pulsars are ordinary rotation-powered pulsars. They're slowing down, gradually losing rotational energy, and that energy powers the radiation we detect. They'll eventually slow to the point where they stop pulsing, at least from our perspective. They'll still be neutron stars, just no longer active as pulsars. Then there are millisecond pulsars. These are old neutron stars that have been spun up, recycled by accreting matter from a companion star. The infalling matter transfers angular momentum, spinning the neutron star up to hundreds of rotations per second. Millisecond pulsars are incredibly stable clocks. Their magnetic fields are weaker than younger pulsars, so they slow down very slowly. They can maintain nearly constant rotation rates for billions of years. There are magnetars neutron stars with magnetic fields even stronger than typical pulsars, 10^14 to 10^15 Tesla. These are the strongest magnetic fields in the known universe. Magnetars occasionally have outbursts where they release enormous amounts of energy in X-rays and gamma rays. A magnetar flare can, in a fraction of a second, release more energy than the sun emits in 100,000 years. In December 2004, a magnetar 50,000 light-years away had an outburst so powerful that it affected Earth's ionosphere. For a moment, Earth's upper atmosphere was disturbed by an event halfway across the galaxy. That's how powerful these objects are. Their magnetic fields are so strong they warp the quantum vacuum itself. And then there are X-ray pulsars, which are neutron stars in binary systems, actively accreting matter from a companion. The infalling matter heats up to millions of degrees, emitting X-rays. The magnetic field channels the material to the magnetic poles, creating hot spots that pulse as the star rotates. Each type tells us something different about neutron stars, about magnetic fields, about accretion, about extreme physics. But let's talk about something even stranger, something that seems almost impossible: pulsar planets. In 1992, astronomers Alexander Wolszczan and Dale Frail announced the discovery of 2 planets orbiting a pulsar called PSR B1257+12. This was shocking. Pulsars are the remnants of supernovae. How could planets survive the explosion that created the pulsar? The answer is, they probably didn't. These planets likely formed after the supernova from the debris disk left behind. They're second-generation worlds born from the ashes of catastrophe. Imagine the environment. A pulsar emits intense radiation. Any planet orbiting it would be bathed in X-rays and high-energy particles. Life as we know it could not survive there. But the planets exist. Wolszczan and Frail detected them through timing variations in the pulsar's pulses, the same technique later used to find planets around normal stars. These were actually the first confirmed exoplanets ever discovered, though they're often overshadowed by 51 Pegasi b found in 1995 around a sun-like star. Pulsar planets are rare. We've only found a handful. But their existence tells us something profound. Planet formation is robust. Even in the most extreme environments, given the right conditions, planets can form. Now here's where pulsars become even more useful to science. Because they're such precise clocks, and because we can observe many of them across the galaxy, We can use them to detect things that affect their pulse timing, gravitational waves, for instance. When a gravitational wave passes through space between us and a pulsar, it stretches and compresses space-time. This changes the distance the pulses have to travel very slightly, causing tiny variations in arrival time. By monitoring an array of pulsars called a pulsar timing array, astronomers can detect gravitational waves from sources like supermassive black hole mergers at the centers of galaxies. These waves have wavelengths of light years far too long for detectors like LIGO to catch, but pulsar timing arrays can detect them. In 2023, multiple pulsar timing array collaborations announced evidence for a background of gravitational waves filling the universe, likely from countless supermassive black hole mergers throughout cosmic history. Pulsars. The remnants of dead stars are now our tools for detecting the faint ripples of space-time itself. It's remarkable, isn't it? We take the strangest objects in the universe, city-sized spheres of neutrons spinning hundreds of times per second, and we use them as instruments, as laboratories, as windows into physics we can't recreate on Earth. And it all started with Jocelyn Bell noticing a bit of scruff in radio data, noticing something that didn't quite fit, following up on it instead of dismissing it as interference. That's how science works: curiosity about the unexplained, persistence in investigating the odd, willingness to consider that the universe might be stranger than we imagine. And the universe is strange, stranger than most people realize. Neutron stars are strange. Millisecond pulsars are strange. Magnetars are strange. The idea that we can use them as gravitational wave detectors is strange, but it's all real, all confirmed, all part of the magnificent, bizarre, beautiful universe we live in. Pulsars pulse, lighthouses sweep. Dead stars spin in the dark, singing songs of physics to anyone willing to listen. And we listen, we time, we measure, we learn. From the ashes of stellar death, we're learning about gravity, space-time, nuclear physics, magnetic fields, and the ultimate limits of matter. But we've journeyed far from where we began, from photons born in fusion through layers and colors and death and remnants. We've watched stars be born, live, and die. We've seen their light carry secrets across space and time. And now, as we near the end of our drift through Starlight, it's time to gather these threads together, to understand what it all means, to feel one more time the connection between the fire in the sky and the fire in our veins. We've traveled far tonight, from the first photon born in a star's core through hundreds of thousands of years of struggle through dense plasma, across millions of kilometers of empty space to the moment it touches your skin. We've watched stars being born from darkness. We've seen fusion ignite, turning hydrogen into helium mass, into energy potential, into light. We've descended through layers: core, radiative zone, convective zone, photosphere, each one a world unto itself, each one part of an elegant structure, billions of years in the making. We've learned to read the language of starlight, to decode the messages written in wavelengths and gaps, to understand what distant suns are telling us about their temperature, their chemistry, their motion through space. We've traced the life cycle of stars, from main sequence stability through red giant expansion to final death, gentle for some, catastrophic for others. And we've met the remnants: white dwarfs cooling slowly, neutron stars spinning impossibly fast, black holes where matter disappears from the universe. It's been a journey of billions of years compressed into a single night, a journey from the beginning to the end of stellar life. But now, let's bring it home. Let's make it personal. Because this isn't just a story about distant objects burning in the void. It's a story about you, about where you came from, about what you're made of. Right now, as you listen to these words, there's calcium in your bones. Strong, solid structural calcium holding your skeleton together. That calcium was forged in the helium-burning shell of a red giant star billions of years ago. a star that swelled, cooled, puffed off its outer layers, and died, leaving that calcium drifting through space. The iron in your blood, the iron that carries oxygen from your lungs to every cell in your body, was created in the final moments of a massive star's life. In the seconds before it exploded as a supernova, when silicon was fusing into iron in its collapsing core. That iron was expelled into space at thousands of kilometers per second. It drifted for millions of years. Eventually, it became part of the molecular cloud that collapsed to form our solar system. It ended up in Earth. And eventually, through billions of years of geology and evolution, it ended up in you. Every breath you take contains oxygen. Oxygen fused from helium in the cores of massive stars. Oxygen released when those stars died. The carbon that forms the backbone of every organic molecule in your body, every protein, every strand of DNA, every neurotransmitter, every thought you've ever had, that carbon was made in stars. 3 helium nuclei fusing together through the triple alpha process, creating carbon at temperatures of 100 million degrees. The nitrogen in your DNA, the phosphorus in your ATP, the sulfur in your proteins, all of it was made in stars. And the really heavy elements, the gold in jewelry, the silver in coins, the platinum in catalytic converters, the uranium in nuclear reactors. Those were made in the most extreme events in the universe. Supernova explosions, neutron star collisions, moments of such intense heat and pressure that even energy-costing fusion reactions could occur. Every element heavier than iron in your body, and there are traces of many, was forged in stellar catastrophe. You are quite literally made of stardust. Not metaphorically, not poetically, literally, chemically, atomically. The atoms in your left hand probably came from a different star than the atoms in your right hand. You are a mosaic of multiple stellar generations, assembled over billions of years, shaped by chemistry and biology, into something that can think and feel and wonder. Carl Sagan in his series, Cosmos, said, "At best, the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies, were made in the interiors of collapsing stars. We are made of star stuff." It's one of the most profound truths in all of science, and it's completely verifiably testably true. We know this because of spectroscopy, because we learned to read Starlight and discovered the same elements there that we find in ourselves. We know this because of nuclear physics, because we calculated what happens in stellar cores and found that the predicted abundances match what we observe in the universe. We know this because of supernova studies, because we watched stars explode and detected the elements they created in their final moments. Every line of evidence points to the same conclusion. We are the children of stars. We are made from their ashes. And here's something beautiful about that. Something that makes the universe feel less empty, less cold, less indifferent. It means we're not separate from the cosmos. We're not strangers in a foreign land. We're part of it, literally part of it. Made from the same processes, governed by the same laws, connected through chemistry and physics to everything that has ever existed. When you look up at the stars, you're not looking at something alien. You're looking at your relatives, your ancestors in a sense, the furnaces that forged the elements that made you possible. There's a kind of kinship in that, a connection that transcends distance and time, and it goes both ways. Because just as stars made us, we are in a very real sense the way stars understand themselves. We are matter organized by the laws of physics and biology into a form capable of consciousness, capable of looking up, capable of wondering, capable of doing science. We are what happens when stellar dust spends 4 billion years organizing itself into complexity. We are how the universe examines itself, questions itself, tries to understand where it came from and where it's going. There's something almost miraculous about that, isn't there? That the universe created stars, and stars created heavy elements, and those elements organized into planets, and on at least one planet, They organized into life, and that life evolved consciousness, and that consciousness developed science, and science figured out where the elements came from in the first place. The circle closes, the loop completes. Stars create elements. Elements create life. Life creates consciousness. Consciousness discovers stars. It's a story, the grandest story ever told. And it's not mythology. It's not legend. It's fact. It's the history of everything written in atoms and light and the slow, patient unfolding of physical law. Now let's think about time for a moment. The light from Betelgeuse, that red giant in Orion, takes about 650 years to reach us. When you look at Betelgeuse, you're seeing it as it was in the 1370s, during the height of the Renaissance, before Columbus sailed, before the printing press. If Betelgeuse exploded as a supernova tonight, we wouldn't know for 650 years. The light from that explosion is still en route, still crossing the void. And it will explode probably soon by astronomical standards. Maybe it already has, and we just haven't gotten the news yet. When it does, it will be spectacular, visible in daylight, brighter than the full moon, a new star appearing in the sky, hanging there for weeks, before slowly fading. Ancient peoples would have called it an omen, a message from the gods, a sign of change or doom or transformation. We know better. We know it's just a star dying, a natural process, physics playing out on a grand scale. But maybe they weren't entirely wrong. Maybe it is transformative, not in a mystical sense, but in a real one. Because when Betelgeuse explodes, it will scatter its elements, carbon, oxygen, nitrogen, all the products of its long life into space. And those elements will eventually be incorporated into new stars, new planets, maybe new life. Betelgeuse's death will seed the birth of future worlds. Its atoms will become part of something else, something new. That's transformation. That's renewal. Just on timescales our ancestors couldn't have imagined. And here's something to think about. The sun is middle-aged. It's been on the main sequence for 4.6 billion years. It has another 5 billion years to go. In 5 billion years, it will swell into a red giant. The inner planets will be consumed or sterilized. Earth, if it survives, will be uninhabitable. If humanity, or whatever we evolve into, still exists, then we'll need to have moved elsewhere. Mars won't be far enough. We'll need to be in another star system entirely. That gives us a deadline, a very distant deadline, but a real one. Leave Earth's solar system or perish when the sun dies. It's a sobering thought, but also in a strange way, an inspiring one, because it means we're part of a larger story. We're not just living on Earth. We're living in a universe that's constantly changing, constantly evolving, constantly creating and destroying and recreating. And if we're smart, if we're wise, if we survive our own self-destructive tendencies, we might one day spread to other stars. We might become a multi-star species. We might carry the story of Earth, the story of this pale blue dot, where life first learned to understand stars to other worlds. We might become, in a sense, Starlight made conscious, spreading through the galaxy, carrying the legacy of our stellar ancestors with us. It's a big dream, maybe an impossible dream. But then again, 100,000 years ago, it would have seemed impossible that creatures barely different from apes would one day decode starlight, would figure out fusion, would understand the life cycle of stars. We've done impossible things before. Maybe we'll do them again. But even if we don't, even if humanity ends here on this one planet, in this one solar system, around this one unremarkable yellow star, we still did something remarkable. We figured it out. We understood. We looked up at the lights in the sky and wondered what they were, and we didn't stop until we knew. We learned that stars are not eternal, that they're born from gas and dust, that they burn through fusion, that they die sometimes gently, sometimes violently, always enriching the universe with the elements they created. We learned that we're made from those elements, that we're connected to stars not just by gravity and light, but by chemistry, by substance, by the actual matter we're made of. We learned to read the secret language of starlight, to decode temperature composition, motion, distance, all from patterns of wavelengths. We learned that the universe is older and larger and stranger than we ever imagined. That there are neutron stars spinning hundreds of times per second. That there are magnetars with magnetic fields strong enough to disrupt atomic bonds. That there are black holes where space-time itself breaks down. We learned all of this in less than 400 years, from Galileo's first telescope to modern space observatories. 4 centuries, a blink in cosmic time. And we learned it by doing what we're doing right now, by looking, by questioning, by refusing to accept ignorance as final, by listening to what Starlight has to say. So, the next time you step outside at night, take a moment, look up. Find a star, any star. And remember that light left the star years ago, maybe centuries ago, maybe millennia ago. It crossed an ocean of emptiness to reach you. And encoded in it, in its wavelength and intensity and spectrum, is a message about temperature, about composition, about the star's life stage and mass and motion. A message that says, I am here, I am burning. I am transforming hydrogen into helium mass, into energy, darkness, into light. I am a furnace, an engine, a beacon, and you are my child, made from my ashes, carrying my legacy, wondering about me across the void. We are not separate. We are connected, always have been, always will be. That's the secret hidden in Starlight. That's what the stars have been trying to tell us all along. We are not alone in the universe. We are the universe. We are what happens when Starlight remembers itself. When atoms forged in fusion, organized by gravity and time and chance, become capable of looking back at the stars and saying, I understand. I know where I came from. Thank you. Thank you for drifting with me tonight, for letting curiosity lead you through fusion and layers and spectroscopy and death and pulsars and this final beautiful truth that we are all, every one of us, made of light, made of stars, made of wonder. Sleep well, dream gently, and when you wake, perhaps you'll look at the sunlight differently. Perhaps you'll remember that it's not just warmth, it's time, history. A photon's 100,000-year journey from core to surface, then 8 minutes across space, arriving just in time to touch your face and remind you, you are stardust learning to shine. Good night. If this journey through Starlight touched something in you, if these quiet hours spent exploring the universe felt like home, there will be more nights like this, more stories to tell, more secrets to uncover. The universe is vast and we've barely begun. Until we drift together again, stay curious, stay wondering, and keep looking up.